ఇప్పుడు మాట్లాడండి.
Good morning, sir.
Good morning. Am I audible?
Yes, sir. Yes, sir.
అక్కడ ఆఫ్ చేయండి మేడం.
Good morning, sir.
Good morning.
Sir, shall we start the program, sir?
Yes, please.
Okay, sir.
Good morning, sir. Good morning, one and all. It's a great pleasure to welcome you all to this 10-day Gian workshop on the robotic head, sensing and processing inside the head of future intelligent robot. We are genuinely delighted to welcome such a passionate and diverse group of participants eager to engage, learn, and grow together. A heartfelt thank you to our organizers and speakers for making this event possible. We hope you find the session insightful and filled with practical takeaways. Let's begin and make this a valuable learning experience. Now I invite the dignitaries onto the dais. I would like to invite our Honorable Director, Sir, Professor Bidyadhar Subidhi, Sir, to join us online. I would like to invite Dean IRAA, Professor S. Srinivas Rao, Sir. Please come on to the dais. I would like to invite Dean R&D, Professor Sonavani Shirish Hari, Sir. Please come on to the dais. I would like to invite our beloved Professor Dr. D. Vakla ma'am, to please come on to the dais. Welcome them with a big round of applause. This is honor to invite our guest resource person, Professor Bhaskar Chobe, sir. Please come on to the dais. Finally, I would like to invite our GAN course coordinators, Professor P. Murlidhar, sir. Please come on to the dais. I kindly request all the dignitaries on the dais to lighten the lamp. We'll start the inauguration with Vande Mataram song.
Vande Mataram, Vande Mataram, Sujalam Sukhalam, Malayaj Sheetalam, Sasya Shyamalam Mataram, Vande Mataram, Shubhrajyotsna Pulakitayamini, Pullakusumita Drumadala Shobhini, Suhasini Sumadhura Bhashini, Sukhadam Varadam Mataram, Vande Mataram, Vande Mataram.
Now I kindly request all the dignitaries on the dais to lighten the lamp. I request our Honorable Director, Professor Bidyadhar Subidhi, sir, to share his views to the participants.
Very good morning to all. I am glad that the Department of Electronics and Communication Engineering of the Institute has taken a very proactive role in organizing this GAN program on robotic head, sensing and processing inside the head for future intelligent robot. So I believe that this is a very upcoming area where robotics and automation has a lot of role to play for the recent need for the future modernization of technology. For example, we may see that the today's surgery, robotic surgery, and which needs a very precise kind of position control. And also you could see that this is very much progressing around the world, and we at NIT Warangal is also a part of this endeavor, and I congratulate the coordinator Professor Murli for conceptualizing this program along with his GAN collaborator, and I also join with all the delegates and the department to welcome our foreign delegate to be here with us. So I believe that the delegates or the participants for this program will immensely benefit by listening to these experiences of these both the foreign expert as well as the Professor Murli. So I also expect that not only in terms of attending the course, but also in the stay in the campus and visiting the department will be immensely beneficial to you and the department as well. Please find the possible opportunity, how best you can connect with the department so that we can take up in future occasions any higher learning landscape. For example, any sponsored research or maybe a joint program, academic program you wish to pursue at NIT Warangal. I also thank our the Dean Alumni and International Relation, Professor Srinivas Rao and Professor Siri Sonwani and the head Vakula Madam for supporting this endeavor of the coordinators to make it truly meaningful, and the disseminations I believe will be beneficial to all the participants. I wish this program to be a grand success. Thank you very much.
Thank you, sir, for enlightening us with your valuable words. Thank you once again, sir. Now I invite Professor P. Murlidhar, sir, to provide us with an insightful overview of GAN course.
Good morning, all. Respected Honorable Director, sir, Vidyadhar Subudhi, sir. Guest of honors, Professor S. Srinivas Rao, sir, Dean International Relations, Alumni Affairs, Professor Sirish Sonavane, sir, Dean Research and Development, and Professor Vakula Madam, Head of the Department of ECE, and Chief Guest of today's function, Professor Bhaskar Chaube, International Faculty, the Chair of Gian University, Germany. It is my privilege to give the overview of this course. So mainly why we have selected this topic, the title, the robotic head processing, signal processing, sensing and processing inside head of a future intelligent robot. So mainly the AI and robotics, the revolutionizing industries and transforming the way we live and work. So the processing systems that are present in the current generation are processing the sensors, with processing the sensors whatever it is available. The modern systems follow the one human architecture and relay data from sensors However, the vast diversity and volume of sensor data make edge computing for robotic heads challenging the future demands. The compact low power systems integrating sensors, memory and processing to achieve the computing and electronics must evolve, leveraging AI to process sensory signals efficiently. The course explores the intersection of sensor technology, computing, AI and focusing on edge advanced processing systems for robotic applications. It provides an in-depth understanding of sensor signal processing, physical sensor technologies and their integration with the modern chip architectures for computation and memory. The course also covers advanced AI and machine learning techniques for efficient sensor interfacing, fostering holistic approach to sensor-driven computing. The primary objectives of this course are mainly the past, present and future hardware software co-design for robotic heads, physical quantities and their measurement, and measurement errors and calibration standards, optical sensors, digital cameras and related deep learning, chemical sensors, mass sensors, pressure sensor, gas sensors, microelectromechanical sensors, sensor interface circuits and their physical implementations, neural networks for sensory signal processing, neural networks for hardware design. So we planned this course for 10 days with 40 hours. Out of these 40 hours, so 26 hours for theory lecture hours and 14 hours for tutorials. So out of these 26 hours, all complete 26 hours, the international foreign expert, so he is highly qualified and experienced, and expert is going to deliver the lectures. All 26 theory lectures is going to deliver, and remaining the 14 tutorials, the 14 tutorial hours. So Sarah is going to take, international expert Sarah is going to take 5 tutorials, and the remaining tutorials, myself and P. Sri Rao sir, we are going to handle these tutorials. All the tutorials we are going to conduct in the MSD lab on Cadence software, and the remaining lecture hours will be conducted in this hall only. So the course starts with an introduction to computing 4.0 and robotic head. Then it gives understanding of designing robotic eyes to enhance visual clarity, learning about noise, imaging and pixel design and image sensor chip. Then moving to light and wide dynamic range imaging, robotic imaging system architectures. Then it will explore sensor properties and signal conditioning and numerical exercises and sensor signal processing. The concept of robotic skin introduces temperature and heat sensing, while practical exercises on temperature sensing. And then robotic nose add another dimension, enabling the detection of environmental factors through chemical and gas sensing. The course analyzes lump parameters in sensor design, which is crucial for improving sensor accuracy. Additionally, micromechanical and pressure sensor play a vital role in touch sensitivity. The course focuses on pH sensing and introduces neural networks for sensory processing, leading to advanced applications such as FPGA-based neural network hardware. Then the course covers the robotic brain with hardware design for neural networks and neural networks for sensory processing. Finally, the course delves into memory stress in neural networks and groundbreaking advancements for AI and robotics. The course is actually more relevant to the current trends and the technology, and mainly we might have observed this AI, how it is penetrated into our day-to-day life, and AI-driven robotics have many applications. So like in healthcare applications, manufacturing industries, and transportation and home automations. So then your participants are going to be learn the complete how to process the data locally, the edge processing, because earlier we used to process the data cloud-based processing. The cloud-based processing, so it is we cannot rely all applications on cloud-based processing. So because there will be a sensitive data, security issues, and also there may be latency or real-time applications, we cannot rely on cloud-based processing. So instead of that, the edge processing, so but that edge processing, that vast data is present, at that with advancements in technologies. So this data processing makes a challenges in edge computing. So that you are going to learn in this course. So how to process data locally in edge computing devices. So thank you. So wish you all the best.
Thank you, sir, for the complete insight about the course and its importance. Now I request Professor D. Vakla ma'am to share the insightful thoughts.
Honorable Director, sir, Professor Vidyadhar Subudhi, and today's chief guest of the function, and also our proud alumni, Professor Bhaskar Chaube, sir, our local coordinator Gian program, Professor, and Dean IRAA, Professor S. Srinivas Rao, sir, Dean R&D, Professor Sirish Sonewala, sir, and the coordinators of the course coordinators of the program, Professor P. Muralidhar and Professor P. Srihar Rao, dear colleagues and participants and all the invitees, a very warm welcome and good morning to one and all. Now today in this inauguration function of the 10-day Gian program on robotic head sensing and processing inside the head of a future intelligent robot, I take the privilege of introducing the Department of ECE to one and to all. National Institute of Technology, Warangal was established in the year 1959, and the Department of Electronics and Communication has been one of the key departments of the institute since its inception in the year 1971. The department has expanded steadily over the last few decades and is now recognized as one of the India's leading academic and research centers. The department has strong liaisons with academics and industry across the globe. The department also provides support to R&D organizations. The faculty is actively engaged in providing solutions to industry problems as consultants. The department academic programs are rated among the top in the country. The graduating students are also well placed in leading academic institutes, research organizations, and industries. And now coming to the history of the department. Initially in the year 1966, MTech Electronics and Instrumentation program is started. And in the year 1971, BTech Electronics and Communication Engineering program is started. In the year 2000, MTech VLSA program is started, VLSA system design. And in the year 2006, MTech Advanced Communications is started. And in the year 2023, another new BTech program is introduced with BTech ECE with honors in VLSA design and technology. And in the year 2024, the existing MTech program, Electronics and Instrumentation, is renamed to meet the present-day challenging demands and present-day developments. It is renamed as Embedded and Machine Learning Systems. And all the programs are top among the country, and there are very good number of students joining with a lot of interest, and all the seats are, there's a lot of demand for these programs also across the country. The department has 39 well-experienced and qualified teaching faculty, and also 13 experienced non-teaching staff. Faculty have the expertise in various domains like VLSA, signal processing, embedded systems, and communications. The department has 180 research scholars and 188 postgraduate students and 689 undergraduate students. The department has 17 well-equipped state-of-art academic laboratories. In addition, the department also has Center of Excellence and research laboratories like 5G Communication Lab, Wireless Communication Lab, Mixed Signal Design Lab, Analog IC Design Lab, and System on Chip Lab are some of the few labs. And we also have other Center of Excellence also. Laboratories are well equipped with the latest software tools like CAD and Synopsys, Mentor Graphics, Xilinx, Vivado, And hardware equipment is also there, like 3D printer, RF generator, spectrum laser, industry compatible FPGAs and drones, etc. And the department is also well equipped with LCD projectors and good furniture, digital class facilities, AC conference hall is also available in the department, which we are having the inauguration program now. And the faculty actively carry out research in various domains, which resulted in 28 ongoing funding projects and from several funding agencies. And regarding the projects, I had to mention that yesterday our course coordinator has secured a project worth 20 lakhs from IIT Mandi. You can give a big applause to the course coordinator. The faculty get several projects from SERB DSA, funded by SERB DSA, ISRO, DRDO, MIT, IIT Hyderabad, DST. And there are good number of publications, yearly publications, more than 450 publications from the EC department. And many patents are also granted, and startups are also there from the EC department. The academic programs of the department are rated among the top in the country. The graduating students, PG students, are well placed in leading industries including Intel, Qualcomm, Texas Instruments, CAD and SanDisk, Xilinx, Synopsys, etc., along with software companies like Oracle, Goldman Sachs, Microsoft, MathWorks, etc. And there is a good placement record for the ECE students, both the UG and PG, and the highest CTC is 88 lakhs. Thank you. This is a brief overview of the department. Thank you for giving me this opportunity.
Thank you, ma'am, for enlightening us with all the departmental activities. Now, I request Dean of IRA, Professor S. Srinivas Rao, sir, to speak few words regarding this.
Good morning to all. Respected Director Professor Vidyadhar Subodhi and highly distinguished and esteemed alumni Professor Bhaskar Chaube, Chair of Institute of Analog Circuits and Image Sensing, Gian, Germany, and Head of the Department Professor V. Vakula, Course Coordinator Professor Muralidhar, and other faculty members of ECE department, and dear participants, research scholars, and all other faculty members who have joined here for attending the inaugural function of this 10-day Gian course on robotic head sensing and processing inside the head of a future intelligent robot. Professor in Department of Electrical Engineering, and I am presently holding the Dean International Relations and Alumni Affairs in the Institute, and this Dean office looks after two things, that is international relations as well as alumni affairs. So briefly I will give about the activities of our office and about this course in detail. So along with all other 5 deans, this 6th Dean International Relations and Alumni Affairs was established in the Institute to look after international relations and alumni affairs. So alumni chapters are spread across the world. 22 are in India and 6 chapters are abroad. All the chapters are working very well, and they are doing their level best and contributing the development of the institute whenever it is required and whenever they feel to assist the institute for developing activities. So out of this, today has shown a lot of interest and coordinating with the department for submitting the Gian proposal and getting sanctioned by the government of India, and coming all the way from Germany to grace this occasion and to deliver lectures on 10-day Gian course. So with reference to international affairs, is handling the government of India sponsored programs like Gian Global Initiative for Academic Networking and Spark Scheme for Promotion of Academic and Research Collaboration, UK India Education and Research Initiative, Heritage Erasmus Mundus, BRICS, DAD, MITAX, etc. Along with these Government of India sponsored programs, NIT Warangal is working sincerely for availing all possible collaboration with various international universities and institutions for collaborative research, faculty exchange programs, student exchange programs under the constant and continuous directions and encouragement of our esteemed Director Professor Vidyadhar Subudhi. Now, regarding this Gian course, it is my duty to once again remind the objectives and outcomes of this Gian program. Gian, this global initiative for academic networking, is approved by Government of India in 2015 in higher education, aimed at tapping the talent pool of scientists and entrepreneurs internationally to encourage their engagement with the Institute of Higher Education in India. To augment the country's existing academic resources, accelerate the pace of quality reforms and elevate India's scientific and technological capacity to global excellence. With this aim, it is started with the following objectives, such as to increase the footfalls of reputed international faculty in the Indian academic institutes, provide opportunity to Indian faculty to learn and share knowledge and teaching skills in cutting-edge technologies, to provide opportunity for Indian students to seek knowledge and experience from reputed international faculty, to create avenue for possible collaborative research with international faculty, to increase the participation and presence of international students in the academic institutes, opportunity for the students of different universities and institutions to interact and learn subjects in the most advanced areas through collaborative learning process, provide opportunity for the technical persons from Indian industry to improve understandings and update their knowledge in the relevant areas, motivate the best international experts in the world to work on problems related to India, develop high quality course materials in academic areas in the form of video recording, live webcast, and it can also be used by a large body of students and faculty to document and develop new pedagogical methods in emerging topics of national and international interest. NIT Warangal has successfully completed Gian Phase 1, Phase 2, Phase 3 with a total courses of 83. In 2015-16, 27 courses were sanctioned under Gian Phase 1 with a budget of 1.87 crores. In 2017-18, 41 courses were sanctioned in Phase 2 with a budget of 2.48 crores. In 2019-23, 21 courses were sanctioned under Gian Phase 3 with a budget of 1.41 crores. In 2024-25, till now 23 courses were sanctioned with a budget of 1.45 crores, and few courses are under review. They may be expected. So till now, under this Phase 4, we have 13 courses were successfully completed and 10 courses are yet to be completed in June. In the Electronics and Communication Department, got six courses, and 4 courses were successfully completed by the coordinators of C.H. Ramarao, Dr. R.L.N. Sai Prakash, and Professor Kalpana, and this is the 4th course. Professor Muralidhar is conducting. 2 more courses are pending. One is Professor Sai Prakash, and other one is Frakrudi. So our special thanks to Director IIT Hyderabad and Dr. Anil Agarwal, National Coordinator of Global Initiative for Academic Networking at Hyderabad. Gian 4 office is working at Hyderabad under the National Coordinatorship of Dr. Anil Agarwal and his team. They are working hard to review to make arrangements for review of the courses approved and speeding up of the process for completion of these courses and regularly monitoring of the activities of each course. So our special thanks to them. Till now, in Gian Phase 4, out of these 23 courses sanctioned, Electrical Department got 7 courses, and after that ECE Department was sanctioned 6 courses. In total, around 48 countries, foreign faculty are collaborated with NIT Warangal under these GAN courses from different countries like UK, USA, Australia, Belgium, Israel, Canada, Singapore, Germany, Italy, Japan, Malaysia, Europe, Norway, Portugal, Romania, Russia, Slovakia, Sweden, Taiwan, Greece, Denmark, France, England, Scotland, Finland, Middle East, and Trinidad and Tobago. In the recent past, many faculty from the foreign faculty are visited for various purposes, such as Spark courses as well as GAN courses and other collaborative works, such as Professor Rahul Rai from Department of Automotive Engineering, Clemson University, USA, Professor Alfred J. Kalyanapu, University of Tennessee, USA, Professor Dr. Tanya Datta, University of Tennessee, USA, Professor Gian Shawar, University of Tennessee, USA, Professor Vijay Raghavan, McGill University, Canada, Professor Maxim Shatov, University of Cytology of Russian Academy of Sciences, Professor Shrikant Joshi, University of West Sweden, Professor Channapat Paniswas, Queen Mary University, London, Professor Indrajit Chaube, University of Connecticut, USA, Professor Tarun Ratanraj, University of Edinburgh, UK, Professor Xiu Yan, School of Electrical and Electronics Engineering, NTU, Singapore, Professor Rahul Jain, National University of Singapore, Professor Ranjit K. Soman, Delft University, Netherlands, Professor Leon, University of Twente, Netherlands, Israel Cohen, Technion University, Israel, Professor Rukmi Datta, School of Electrical and Telecommunication Engineering, University of New South Wales, Sydney, Professor Yao Ming Chen, National Taiwan University, Professor Jim Ching Jan, National Taiwan University, Professor Suresh Gade, University of Ottawa, Canada, Professor Muhammad LSC, National Koh-Sing University of Science and Technology, Taiwan, Professor Edris, Professor in Department of Electrical Engineering, Lato University, Finland. So all these faculty are visited and interacted the faculty members of concerned departments and research scholars as well as the participants. With all these interactions with all these faculty members, so all of you have got a lot of international exposure as well as domain knowledge. So it will be definitely useful for future research collaborations as well as student exchange programs and many other things. So regarding this course, robotic head. So we all know that robotics are entering in all the fields for various works, particularly for sensitive works. They are very much preferred nowadays. So this program, whatever contents was elaborately explained by Professor P. Muralidhar, and those contents will be definitely useful for all the participants as well as research scholars and faculty members who are attending from this institute along with ECE department faculty. Definitely it will be very much useful and a lot of knowledge you all will gain by interacting and listening with Professor Bhaskar Chaube. He is very well known among the student days also. He is having a lot of innovative thinking, research attitude as well as sincere and hardworking those days. So we are very much proud of an esteemed alumni like Bhaskar Chaube, and we are all very fortunate to interact with him and listen to him. So our special thanks to Professor Bhaskar Chaube. Wish you all the best to all the participants. So these GAN courses are monitored by the Dean IRA office along with the Dean Research and Development. So all these all the financial things as well as academic things are monitored by Dean P&D, also along with Dean IRAA. So our special thanks to Professor Sirish Sonevane for speeding up of the process by meeting the targets of national coordinator who is sitting at IIT Hyderabad, Dr. Anil Agarwal. They are closely monitoring each and everything, and our Professor Sirish Sonevane is working hard to handle these things very nicely and effectively by meeting the targets with reference to time. So my special thanks to our Dean Sirish Sonevane also. Thank you one and all. Wish you all the best to all of you.
ఆన్ చేయండి అక్కడ ఆన్ చేయండి చేయి రావటం లేదు యా దట్స్ ఓకే ఓకే
Thank you, sir, for enlightening us about various GAN activities on the campus and for your encouragement. I request Dean R&D Professor Sonavane Shirish Hari sir to speak few words regarding this.
Good morning. Professor Biddadar Subudhi sir, Professor Bhaskar sir, international faculty, Professor Vakula madam, head of department, Professor Murlidhar, my colleague Dean IRA, and other colleagues from departments, Professor Anjanelu, Sai Prakash sir and others. Good morning. See, these are programs, the Gian has started I think 2016 onwards, which is specifically made for the academic networking. So, it has, we almost, I think in the institute, it is more than 50 programs have already been conducted. Each department, I think, conducted minimum 5-6 programs. So we are quite ahead in that networking program. I especially thanks to Professor Bhaskar for, accepting the invitation and, to plan this program and helping to make this happen. I welcome you, sir, again to NIT Warangal, and thank you for accepting the invitation. Just to have information about what activities these things have been happening, I will not take much time, but it should know for all of us that how we are progressing actually. If you look this year, we have having the research grant sanction amount is 42 crores. Most of the grants, if you look, the 5 crores itself has came from the EC department. There is the highest contribution, I would say. Almost near the faculties, 5 faculties which have the DOT projects actually. These are new faculties. They have joined and they got these, projects. As well as the consultancy grant is around 4.2 crores, which is going to be reached this year first time in NIT, that will reach to the 5 crores. For consultancy. Patents, we have filed more than 50, accepted, granted patent more than 50. This year itself, 2024, we have granted more than in our IT. There is also startups, if you look, earlier very few startups were there, but now we are in the 28 startups have registered under NIT Warangal. We have founded an Section 8 company, what is called NIT Warangal Innovation and Entrepreneurship Foundation. This foundation will help us to promote the innovations and entrepreneurship. So there are also what is called through this Spark and Gian programs, this networking is very important, and number of students, PhD students are started visiting abroad and started networking with the other faculties, as well as faculties are already been earlier visiting. So this is very much important. Startups are also been started by the PhD students. So I request those who are PhD students are there, try to see that how we can best file the patents out of your research work. Maybe you can take the help of our CII. So MTech and PhD students, I request them to see how we can able to see the file the patent through this one. Mighty Genesis funds are available, as well as our notable alumni. Dr. V.A. Shastri recently has given 50 crores. Mighty Genesis also, we have almost 1.5 crores to only promote these startups. Okay, so these are some of the activities, and I wish you all the best for all of you. and try to make the networking, okay? So these are just, I think Gians are the just important motivations. Be connect with Professor Bhaskar and make the connectivity better. Dad Spark is also new program is coming up. So there are certain steps are there. Once you have these Gian programs, later there will be possibility that how the Spark DAD networking has come up. Again, there will be possibility at higher order, networking will be there. So you be ready. And I request all the PhD students to try to be involved. These are the unique opportunities for all of us to meet the professors. Earlier time, we need to go abroad and just attend the lectures. Now the professor itself in the campus, try to be with them. That their presence itself make a lot of values to additions to us. Okay. Thank you, Professor Bhaskar, for be here, and thank you all of you. Bye. Thank you.
Thank you, sir, for enlightening us with all the research activities going on the campus and for your encouragement. Now I request Professor KLV Sai Prakash Sakuru, sir, to introduce the guest.
Yeah, good morning. It is my honor to introduce our distinguished guest, Professor Bhaskar Shobe. Professor Bhaskar Shobe Professor Bhaskar Shobe has been a chair professor in electrical engineering at the University of Systems, Duisburg, Germany from Jan 2020 to June 2021. Previously, he was an associate professor of engineering sciences at the University of Oxford and a tutorial fellow at Somerville College, Oxford from Feb 2013 to June 2018. Before that, he was a lecturer at the School of Engineering, University of Glasgow, UK from May 2009 to February 2013, and a research assistant in engineering sciences at the University of Oxford from August 2006 to April 2009. During this period, he also served as a college lecturer in engineering science and Fulford Junior Research Fellow at Somerville College, Oxford from October 2007 to April 2009. He is also a holds a visiting position. He has held several prestigious visiting positions worldwide, including visiting fellow at Nazarbayev University, Astana from February to March 2018. Marie Curie Fellow at Tattle SRL, right? Yeah, Italy from July 2017 to Jan 2018. International Visiting Fellow at the University of Sydney, Australia from October to December 2009. Microsoft Inspire Lecturer at the School of Economics and Decision Science, Northwest University at Mafeking Campus, South Africa from August to October 2007. Guest scientist in psychophysics, neurophysiology at the Max Planck Institute of Brain Research, Frankfurt am Main, Germany from April to December 2005. He got his doctoral degree in engineering sciences from the University of Oxford, UK, where he was a Rhodes Scholar from 2002 to 2006. He completed his Masters of Arts from Oxford in 2013 and his postgraduate certification in academic practices from Glasgow in 2012. He graduated from ECE NIT Warangal from 1998 to 2002 and was awarded the gold medal for best outgoing passing out student. During his graduation, he received a merit scholarship awarded to the top 10% of students and an award-winning final year project. Professor Shobe has received numerous awards and honors, including IEEE Censors Council Early Career Achievement Gold Award in 2011. He was the winner of the Europe-wide decision contest in 2008. He received AC Irwin Award, University of Oxford 2006. He received Research Student Award, Image Systems Group, Royal Photographic Society, London 2005. He received the Thomas Award, Institute of Electrical Engineering, London, UK 2005. It's taking a long time because he received numerous scholarships and sponsorships like Euro Practice, Hilsilcon sponsorship in 2021, Raymond Davis Scholarship USA in 2006, Jagdish Bose National Science Talent Scholarship India in 1997 to 1998, and many more. Senior member of IEEE, a fellow of Higher Education Academy UK, and a fellow of Institute of Engineers and Technology IET UK. He has secured multi-million euro research funding for projects such as he is the main PI, German Research Council DFG, for 1BT 3D imaging with funding of euros 721K during 2024 to 27. He is the PI, investigator, principal investigator, deputy speaker, and bridge professor for the German Research Council DFG for Learning to Sense DFG research unit with funding of 3.3 million euros with an individual share of 400K euros from 2022 to 2026. He completed 25 research funding projects. He is also an editorial board member of IEEE Sensor Journal from 2015, Frontier in Neuroscience, Neuromorphic Engineering from 2022, IEEE Transactions on Circuits and Systems during 2013 to 2015, special issues on OXCAS, Analog Integrated Circuit and Signal Processing in 2017. He supervised 5 postgraduate research assistants and 9 doctoral students, co-supervised 6 doctoral students, 14 master theses, 11 Master of Engineering thesis. Earlier it is from Gian University, now it is Oxford University, 14 Master and Bachelor thesis from University of Glasgow, 7, and also 7 interns. He has published 49 journal articles, reviewed 35 peer-reviewed conference papers, delivered 43 invited lectures and seminars presentations, contributed to 5 book chapters, presented at 24 conferences, and holds 6 patents. He has played a key role in major international collaborations, advisory roles, and research evaluations of organizations like German Research Council, European Commission, EPSRC UK. With a strong background in academics, research, and innovation, Professor Chaube continues to contribute significantly to the advancements in electrical engineering and AI integrated sensing technologies. With these few words, I now hand over the mic to the speaker, the main speaker, Professor Chaube.
I will speak loudly. Don't worry, I have a history of speaking loudly in this place, so I don't need microphone. So then I can't speak truth. When things are recorded, you have to be a bit posh and polished. So it looks a bit wrong standing on this side of the stage when my teachers are sitting on that side of the stage. So I'm the one generally sitting that side and being annoyed. 6 lectures, 2 more to go before tea. And here's the last person, jo 10 minute aur bore karega, right? Good morning to all of you. I hope during the next 10 days of my stay, some of you would like to hear what I have got to say. If you don't like any of that, we'll go and play football something. Do we still play football in Warangal? Okay, that's good to hear. It was also nice to hear the words highly intelligent and capable from one of my teachers. Last time I was in this building, not in this building, the building next to it, that used to be the old electronics department, I heard the word highly useless and wasting Government of India's money. This was Krishna Prasad, sir, who basically said, look, Bhaskar, you are very intelligent,
drop electronics, write the MSET exam again next year, go and do computer science, you'll be the topper there. And I told, sir, I had an opportunity to change computer science in the first year. I did not. And he was like, useless fellow. What are you doing here? This was the same person who then gave me the keys to the VLSI lab, him and NS Murthy, sir. Now, to some of you, a VLSI lab might be a place to go when your professors force you. In my days, it was one of the coolest places in Warangal. By coolest, I really mean coolest, because rest of Warangal was very hot. And I come from Arunachal Pradesh. For me, February is hot, forget about April. The ECE department had only one building where there was air conditioning, the VLSI lab. So getting lab keys to the VLSI lab is like getting heaven in your life. And that's why I ended up writing papers. Not because I wanted to write papers, I wanted to get away from the heat. So I ended up most of my time in electronics department's VLSI lab. We had early days of Cadence that time. Very early exploring various aspects of Linux operating system, which I must confess, you know how Professor Srinivas Rao sir did not forget mentioning that electrical engineering had the highest number of awards, followed by the ECE. So there's you can see the tradition, right? And so thanks for Professor Siris by saying that electronics got more. That generally does not happen. I mean, things have changed in Warangal from my days. If you're a professor of one department, you think my department is best, everyone else is useless. I mean, that was a word which I learned in Warangal. So similarly, computer science department did not believe in teaching us anything about computer science. But in return, I think electronics didn't believe in teaching them any electronics either. I don't know if things have changed since then. So this is how I ended up doing electronics engineering by constant abuse. And I have just been told that abuse system has stopped. Professors are not abusing students anymore. That's not fair. This was wrong with my generation. So to help my senior professors who taught me and some of the junior people who have joined since I was a student, I continue the tradition. In Oxford, as well as in Glasgow and in Zegan, where I currently teach, I give punishments to my students, including bachelor and master students. Now you know why I can't say things on recorded voice. So we have a punishment policy that you have to do 10 push-ups if you do something wrong, or you have to run around the parking lot. Now, this comes in two ways. If you do something brilliant, you can make me do 10 push-ups. So it's an equal opportunity discriminator, if I can use the terminology. Anyway, it's good to be back here. Things have changed dramatically. For example, the chairs are much better. There's air conditioning in places which are not VLSI laboratories. And it's good to see my senior professors who have taught me over the period of time. Despite the constant abuse in the classroom and laboratories, post-classroom and laboratories, they were the most gentle creatures you can imagine. I mean, NS Murthy sir and KP sir were very nice. I mean, so was everyone else. I mean, I don't know what used to happen when they were taking our examination, as if there was a bug which entered their body. Ask to abuse karke aana to all the PhD master students. But they constantly helped and supported us over the period of time. And I think I abused my professors as well when I was here. I used to ask too many questions. That's why in the end they just said, go and sit in the lab and figure it out yourself. Warangal was a very interesting place for my academic as well as personal growth. I come from a very remote part of India, Arunachal Pradesh. And I will just end this with the last note on how my introduction to Warangal was there. And this might be, so when I entered the building, the REC Warangal yesterday, I still call it REC, that's my college. NIT is not my college. I'm the last batch of Regional Engineering College, and I still like that word better than this IT sounding thing. It sounds like, Information Technology Institute, my apologies. The first thing written was the regulations against ragging. And that reminded me to the old days. My first entry into Warangal was two seniors caught me, and what's the first question you ask a junior? Which state? Right? They asked me which state, and I purposefully said, AP, sir. What's the next question you ask to an AP person? which district, because that will determine how your ragging will continue. I don't know if it still continues or not. They said, which district? And I proudly said, Sir, Papumpare. Next 5 minutes were long abusive statements in Telugu, which I did not understand. Literally, he wanted to say that I'm making a Mickey of him. I mean, there's Godavari, there is Khammam, there is, Chittur, there is no Papumpare in Andhra Pradesh, right? So I'm standing there with my mouth open, young 16-year-old lad from Arunachal Pradesh, like, what the hell? Hey, the place is hot. The way the guy is abusing me, not even in English. Abuse me in English, I can take it. They said, no Telugu? And I was like, no, sir. And then he abused me for 5 minutes in English, saying, A, you take a seat from AP and you don't even speak Telugu. Then I had to translate, sorry, sir, Arunachal Pradesh. That was my introduction to Warangal. It's good to see the tradition of ragging continues to that day. For those of you who might be complaining, a person senior in my batch committed suicide, which was very harrowing based on ragging. So there was quite a strict police presence when I was a first-year student. And then my professors and seniors used to complain. Last year, one guy committed suicide. This year, nothing happened. Ragging has gone down. Thank you very much. I hope you enjoy the next 10 days. Thank you very much.
Thank you, sir, for enlightening with your words. It's time to felicitate our guests. I request all the dignitaries on the dais to felicitate our guests.
So I request all the deans as well as HOD and senior professors to join for felicitation of the guest. Sir, Anjaney, please. Venkay, sir.
Now it's time to vote of thanks by Professor P. Muralidhar, sir.
So good morning once again. So it is my privilege to propose vote of thanks on this occasion. So I extend my sincere gratitude to Professor Vidyadhar Subudhi sir, Director NIT Warangal, for gracing this event online and sharing his valuable insights. Sir, your encouragement and vision continue to inspire us. My heartfelt thanks to Professor Bhaskar Chaube, the Chair of the Institute of Analog Circuits and Image Sensors, Gian, Germany, so for being part of his academic initiative and for his upcoming sessions that promise to enrich our knowledge in this cutting-edge domain. So here I ventured to say the Bhaskar Chaube is my student. So actually I joined in this institute in 1997, but just associated only in the final year lab. But that time I don't know why, but the Lord has given to me the final year lab. So that electron instrumentation lab was associated with other senior professor. Professor G. Vijaya is there. Professor Vijaya and myself as well as Professor T. Kishore Kumar. We are the associating to Professor Vijaya in that lab, electron instrumentation lab. And just only that course only, I just associate with the Professor Bhaskar Chobe. So that way I can say that I am a teacher of the Bhaskar Chobe. So Bhaskar Chobe on those days is a little bit rational thinking type. So that actually instrumentation lab, electronic instrumentation lab. So we have that experiments, the normal procedure is students has to prepare and come to the lab. So we used to give before, so instructions. So you just before for the lab, next lab, the student has to prepare and come for the experimentation. But he came and that day, that experiment is a little bit difficult experiments, and that is completely in enclosed system. That the circuit also completely enclosed, not visible to for understanding or anything, only just by reading the manual only they should experiment that. So then he suddenly, Vijay has not come and myself and Kishore Kumar is there in the lab. So then he stand up, then he said, so how we can do the experiments? So without understanding the circuit internally, that's what he raised his voice that time. So because we are newly joined, that time newly just only, we are also just learning stage only that time. So, but after Vijay has come and Vijay has again explained, and I also maybe with high tone, Vijay answered his questions. Right, sir? Thank you, sir. I extend my sincere thanks to Professor Srinivas Rao, sir, Dean, International Relations, Alumni Affairs, and Local Coordinator of GAN Program, NIT Warangal, and Professor Shiresh Sonavane, sir, Dean, Research and Development, and also in charge directors today, for their unwavering support for making this program success. So both the deans, actually, I want to say one word here, both the deans are down to earth. So they will work very hard. So then whenever we just send a message, SMS, phone call, or even WhatsApp message, they just to attend. Both the deans are same nature. So I'm very thankful to sir for working with you. So mainly the series Sonavane sir, even for even in the coffee time also, suppose if say some important work is the important urgent work, used to sign there itself. So normally, and also one incident I will tell you. So I just went to Dean Series Sonavane sir for some approval. So sir actually he has taken approval from the director and he has taken image of that photocopy and WhatsApp me. So your application is approved. So earlier we used to move around the deans, but the deans are calling and informing us. So your work is done and you can come and collect the things. So that type of the down to earth, these two deans are same nature and we can go at any time and we can interact with them easily. So thank you very much, sir, for gracing these occasions. Even Srinivas Rao, sir, so for his support, continuous, even yesterday, a few days back, continuously, regularly, I'm just sending a mail, immediately he responds, even for SMS, phone calls. So both are very hardworking and down to working teams here, and thank you all. And I'm special thanks to Professor D. Vakula Madam, department. The same nature again, Vakula Madam also. We can walk in the HOD camp, simply just like that. And she is very cooperative, flexible, and she's encouraging nature. And so for her support, I can able to make up this course. So thank you, madam. And my sincere gratitude to course coordinator, Professor P. Patri Srihari Rao, course co-coordinator. Myself and P. Srihari Rao, sir, actually earlier we conducted 2 GAN courses. So from the US process. So this is our 3rd course. So the first 2 courses actually is the coordinator. So from that experience I learned, and again I actually started this course myself, and thanks to Professor Srihari Rao, sir. And thanks to all the participants and management and their principals for sponsoring for faculty to this course. And also my special thanks to my colleagues, the senior faculty members and other department colleagues for attending this function. And also with thanks to all the technical staff of our department, and also office staff of our department, and also thanks to all the PhD scholars, and also special thanks to my scholars. They are actually worked hard to complete special thanks to my scholars like Nandini as well as Gopalakrishna. They worked hard to make this program a grand success. Lastly, I thank organizing committee, technical staff, everyone behind the scene who have worked tirelessly to ensure the smooth execution of today's program. Thank you, one and all.
Thank you, sir. Thank you, one and all. The inauguration ceremony comes to end, and we will close this by national anthem.
जनगण मन अधिनायक जय हे भारत भाग्य विधाता पंजाब सिंध गुजरात मराठा द्राविड उत्कल गंगा विंध्य हिमाचल यमुना गंगा उज्जल जलधि तरंगा तव शुभ नामे जागे तव शुभ आशीष मांगे गाहे तव जय गाथा जन गण मंगलदायक जय हे भारत भाग्य विधाता जय हे जय हे जय हे जय 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 हे
Please join us for a group photo. All the participants, please join us for a group photo.
So all the
Participants, maybe you can join for the group photo. Maybe you can stand on the stage. Please come.
You will not get an email out of the photo. And more because I have reminded them of the old days.
So that's how the threats used to start in Warangal. Professor Bhima Rao sir, he's still around, right? So first lecture of EDC, Bhima Rao sir goes, this is a very hard subject. I worked very hard in my master's and I got 66%, which loosely translated as, come whatever you do, you are not going to get more than 66. And he remained true to his words, I got 66. Okay, can I get a, should I use, आपका machine use करेंगे कि अपना machine use करेंगे? अपना machine use कर सकते हैं? Projector cable लाना होगा ना? नहीं तो उस machine वो क्या office का machine है कि किसी का personal machine है? Personal है तब हटाइए, ठीक है. Problem है ना sir? इधर white board भी नहीं है. White board है? Okay. Worst case में white board में drawing होगा. HTML. Yes. As and when the projector Baba agrees to my demands of showing you something. So part of this course is actually part of something which I am developing to be a textbook for IEEE Censors Council. Because currently we don't have a decent book which covers chip design and sensory chip design at one course. So we have analog IC design courses, we have digital IC design courses, we have robotics courses, we have sensors book. I mean, sensors and automation book is this thick. We don't have something which covers the chip design for electronics engineers. And we are electronics people. We don't like talking about how chemical reactions take place or different materials. There's only one material we know, right? Which is the most commonly used material we use? Silicon. And that's the only one we know about. Let's be honest. If you knew more, we would have done other subjects. Good. So the plan for the course is for 10 days. We are doing a little bit of shift in the planning. Obviously, I was going to be here last day as well, but sir, I have to be in another place. So Professor Murlidhar and Professor Rao will take the last 2 days of the course, and we will go before that. And rather than 4 hours a day, we will increase your workload to 5 hours a day. For a very simple reason, when we start the lab work, it takes a bit time for things to mature. So we'll give you more time in the lab, and that way we'll get enough time in the last day to keep things open or for me to go and sleep, right? And sleeping is also a vital activity of being a professor. Either sleep during the lecture or... Now, what language do we speak here? We speak English, right? If you don't understand my English, do stop me there. My English has become a very strange mixture of English, British English, German English, Indian English. Okay? My Telugu was hopeless and it still is hopeless. So I can try, but will not work. Hindi will come from time to time, so if you don't understand anything, do stop me then and there. Actually, by Government of India policy, if I do the entire lecture in Hindi, I might get a prize, something like that. You might not understand any of it. Let's try again from a different port. Okay, just give me from a different port. I might have to restart my machine. It thinks it has taken because it has changed the... Okay, it is connecting and disconnecting. So this is the computer science revenge on electronics people. Our projectors never work in our department. Let's try that thing. So I will transfer it to a USB disk. So for those of you who are thinking of continuing for next 8 or 10 days or 6.5 days with me, can you just tell me what level you are of studies? Anyone who is bachelor's? One person. Which year? Final year. Then you should know enough, right? Hopefully. Masters? Which masters are you guys doing? Robotics and AI. Then you should know more than in this field, right? Okay. And doctorate level? Rest. Okay. Then we can go a bit more advanced than what I was hoping for. Right, madam? Let's go. सर ये फैन ऑन हो सकता है क्या? नहीं तो ठीक है हम वहीं खड़े रहेंगे. I will stand there, madam. AC आएगा इधर में? ठीक. Copy कर. Now let's copy because otherwise, are we going to use the same machine for all day or just today? आज use करते हैं, and then I will delete it at the end of. So there should be a folder called microsense. कहाँ गया? Right there, it has gone. So for those of you who are getting worried, there is going to be a long lecture. I have exactly 9 slides. Okay. Right, we will keep track of time. We are starting at 11:27. What time is lunch hour? 1 o'clock. In guest house. That's posh. This is not nice. I was hoping you guys will be eating the food which made 99% of us sick and one of us to die. Good. Right. So we are chip designers. For all of those who have got a background in robotics and automation, I'm going to give you a bit of shock. This is not about robotics and automation. The entire course is going to be about things which goes into a robot. So to start with, we somehow have this fascination about humanoid robots, right? Robots which look like us, essentially, which are bipedal, have got 2 hands, and have got a head. I still am trying to understand why do we want to do that, because to be very frank, walking on 2 feet is quite challenging. Walking on 4 feet is nice. Walking on a circular feet is even nice. You can roll anywhere you want. Agreed? But we have this fascination with a humanoid robot, so let's go with a humanoid robot. I'm sure people who work on technology and society can give better answer than I can. Now, if we are trying to make a humanoid head, then we need to, is it on? It is on, okay. Figure out what does a head do. So what does our head do? Thinks, that's a good one. Other than thinking, what does it do? So thinking is processing, right? So it takes that data, and what does it do? What do you mean by thinking? And so we do process the data. What do you do with the data? We try to extract information out of data. Okay? So right now you're looking at me, but you're not just looking at me. You're looking at the screen, you're looking at the projector, you're looking at this whiteboard, you're looking at my shirt. Your brain is ignoring all of this information, right? Just now when I said look at my shirt, all of you guys looked at my shirt. Till this time, you're not looking at that. So brain had figured out this is a useless information. That board is, the eyes are capturing everything. They're like a camera, right? They're capturing everything, but your brain has filtered out this information. It has learned with due course of time how this is not information. So all of this is data, so it extracts information out of data. And then it does something meaningful with the information, right? If it figured out that there's a lion coming in, the meaningful information would be there's a predator coming towards me, and the action would be run if you can. Or if you become like me, then pray, right? You're not going to beat the lion in running. So that's one thing. What else does the human head does? And Babu, by now you realize I'm a professor. I have infinite patience. I can wait. Motion? Emotions. Still part, okay. To some extent, the question which you might ask, are emotions independent action or they are still part of processing? You look at somebody, oh crap. So the other rule which I saw after entering Warangal was ragging, and the other big board was personal display of affection, PDA. I had to figure out the whole thing to read. Oh, wow, we have got regulations against this. So the question still remains, are emotions independent activity or they are part of processing? You see somebody, you feel good. You see, you look at your son or daughter, that affection is allowed, right? One hopes so. So they are still, or you look at a, thing, something you feel like crying, somebody's dead. I think they're still part of processing. I might be wrong, but so question still remains. Now, you guys are thinking the head to be this. There's more to the head. Head starts from here. So now you tell me, what does my head do? I didn't ask what does my brain does. I asked what does my head do? So tell me, what else does my head do? It controls information, so part of data processing, the second stage of data processing. What does it sense? Good. We start with imaging. We have eyes. We have ears. So two senses. What other sensors we have? Taste. We have some sort of chemical sensor. We have skin, what does skin sense? Now we're talking about physical quantities, right? So we started with vision, which was sensing light. We went to sound, which was sensing audio. We went with chemical sensor on our taste. What does skin sense? All of you guys have got this sensor. Tell me, what does it sense? It's a wonderful sensor. It senses many things. What else does it sense? Temperature. Okay, one thing. What else does it? Surface structure. What else does this? Pressure. Well done. It senses pressure. Somebody beats us, we know that, right? What else does it do? Of all the senses we are going to talk about, this is the most complex one, the design, the reverse design. It's not one sensor. It also has hair follicles. So it's time for you to go and figure out what do the hair follicles do. Now, here is a very interesting question we have. So we talked about things which we have, right? Oh, some of you forgot. There's one more sensor which is forgotten. So we looked at tongue, skin, ear, eye. What have you forgotten? Nose. So what kind of sensor is the nose? Kind of a gas sensor. Oh, sorry, a chemical sensor, right? Smell, well, we think so. So at least if you took at the word of panch indriya, you know what we call in traditional science, we have at least 5 different sensors in our human head. Then the question comes, now at least these we should be able to sense using a robotic head. If we want a robot to feel and look like us and do things which we do, this much it should be able to capture. Agreed? So if I make a human head, I have got all these sensors there. The next question to ask, and now I'm going to abuse in the entire computer science department. By now you would have figured out that I love my department and I've been trained by the people here, so what do I do? Where are these sensors located compared to the processor? The processor is the brain. Now I have got a big sensor called skin which is running throughout my thing. But my sensor, the skin sensor on my toe is not as sensitive as my face. Agreed? I mean, some of you might have a very sensitive toe or leg. But generally speaking, our legs are a bit more hard bound than our face. Agreed? I mean, there are people who will walk bare feet on hot road who are going for Sabarimala and this, but if you put the same heat on the face, it will be felt. Okay? So the good skin, the good sensor, the highly sensitive sensor is here. And as we go away from it, either the sensor is bad or there is too much information, there is long distance for the information to travel. So this is something unique which the human body or most nature does. It keeps its good sensors very close to the processor. Agreed? Now think what we are doing in computer science. We are making these huge data clusters, and the idea is you collect information from mobile phones, different sensors, and we send all of this information to a big data cluster, which then processes this information. This is exactly opposite to what the nature did. Now, we may agree or disagree that nature is a good engineer. Right? I mean, nature is a bad engineer as well. Agreed? I mean, think of this way. It has put an appendix, the whole role of which is to kill me someday by bursting. Okay? And there are sensors which keep on degrading. I mean, many of you are wearing glasses. It's a very good example of degradation of sensor in our lifetime. Okay? But this is very interesting. It keeps all its good sensors close to the processor. So it does not want long distance communication of data. So that's slightly different to the way we are doing deep learning right now, or artificial intelligence. Actually, it's very different to artificial intelligence. So nature did not believe in one central intelligence and everything being a terminal of it. It was not a mainframe computer. It was very much distributed intelligence. Every brain has got an intelligence. I think in something, my colleagues in humanities think in something, my chemical engineering colleagues think in, and we all collectively progress our humanity. Whereas the way we are going in deep learning regime is where there's one big machine, giant machine, which collects all the data and does interesting thing to extract information. We don't do that way. So that's the first thing which we have to think very carefully. By doing this small distance communication, we are saving quite a lot of things. We are saving a lot of energy. Now, most of you would have done a lecture on communication theory in your undergraduate. And most of you would have slept in the third lecture of communication engineering in undergraduate as well. You know, when the Cloud-Shannon theorem started. Agreed? At least I was hoping one person to say, no, sir, I really love the theoretical communication engineering. The bottom line remains, for any data to move, it needs energy. So while we were evolving, the nature decided that not to move important information for a long distance. Right? So things are going from here, somewhere here, from eyes, somewhere to the back of our head. That's where our primary visual cortex is. Skin information is moving from all over, and as we go away, our sensitivity starts falling down. So we have agreed on that thing. So this goes to show, if we are going to mimic nature, either we put loads of, and you could say, why don't I have an eye on my knee? It's an important question, right? If I had an eye on knee, I could, or why don't I have an eye at the back of my head? I need to turn my head. Think of it this way, mechanical motion is more energy consuming than having another eye at the back of my head. We still don't know why nature did that, but we know what it did. You believe in nature, you believe in God, whichever 20 million gods you believe in, the argument still remains the same. There should have been a logic behind it, unless of course you believe nature is illogical. So if we are going to mimic that, we need to get all of those sensors at least, and a few more. Now we know nature is not just what we see and perceive, there is more to nature. So we see only visible light, but we know infrared and ultraviolet exist, right? So one would kind of believe that the intelligent robot which we are going to make would also be able to sense these things, right? The other thing which we have as human beings is our sense of anything is not linear. So most of our sensing is either exponential or logarithmic. A very good example would be if the coffee is a little bit hot. Okay, how many are coffee drinkers here? Everyone? It's South India, for heaven's sake. We have to be coffee drinkers, right? I save lots of money by not drinking tea or coffee in my bachelor's. But if the coffee is a little bit hot, you feel it. If it's very hot, you only feel it's hotter. And the hotter it gets, at one point it will burn your teeth, but our sensation is not linear. Same with our skin. I mean, the example I used to give is if somebody punches you on your face with one force and punches you with slightly more force, the effect will be. And same with eyes. I mean, room is a little bit bright. From dark to bright, you feel it. But the brighter you get, you feel less and less of it. Okay? So it's not a linear sensor. Most of the time, it follows Stevens' power law. Right? It's some power function we have. So that's all right. The other good thing which nature had was it had the third dimension. It could design as a 3D structure. Now, as an engineer, we can design things as 3D structures. Somehow we don't like things in the depth. Our mobile phones have kept on shrinking in size, right? Though I must confess, I never understood why, as electronics engineers, we try our level best to make phones very thin, and then our first thing which our customer does is buys these, right? और अगर उससे पेट नहीं भरा तो buy a screen protector as well, a thick one. I mean, tell us in the beginning, we'll make a thick phone. We used to make thick phones. And same with television screens. We used to have thick screens and we want things thinner and thinner. So that's one limitation we have. Now, from microelectronics background, when you're starting making chips, that's other limitation we have. Our chips are not three-dimensional. They are two-dimensional structure. We grow things on a flat surface. Why we do that, we will see a bit later. So now we have this problem is we could need to come up with a chip which not only has the processing part, which was there right in the beginning, but can also do sound, video, or at least one of these. Okay, even if I don't try to make a single chip which matches the human brain, but at least one of these sensors. Agreed? Because only then we will have these chips going into the human head, robotic head, to make a robot out of it. Good. So, and then the next question which we have to ask is how good my sensor should be. Now this is again where we have a bit of a conflict. Because we are designing things to be bought by the market. Okay? If you make the best device in the world, nobody buys, it's useless. At the end of the day, engineers Okay, let me ask this question to you. Name 5 famous scientists which comes to your brain, and I'll just pick random people and you have to name a scientist. The person wearing jagged t-shirt here. Einstein, first name, almost always. You can bet on one of these 2 names which will come the first, right? The lady with a smile, the second person, yes. Yes. Tesla, okay, I was hoping for Newton, but Tesla has come. Fine, we will live with Tesla. And the person with the red shirt. Niels Bohr. And your name was? Madame Curie, okay. Gender equality in action as well. And the lady with the black cloth here. Just sit, don't need to stand. Galileo. Okay, so we have got the 5 famous things. Well done. And all of you are engineering students, right? So next question. Name 5 famous engineers. Let's pick the same people. Vishwesvaraya, all Indians go with that name, right? Civil engineer. I could have restricted the question, name 5 electronics, but let's go with 5 engineers. So we get 1 name, Vishwesvaraya. Second, all those who are quick to name Einstein, Galileo and things. Abdul Kalam, okay, I could give him at least by, both are Indian fame scientists, right? If I ask the same question in Israel, they would have never heard of these people. Agreed? But theek hai, chalo, I will take these 2. Third one? Who the hell is he? Sigma AI. New startup, right? A space scientist, and you use the word scientist. I didn't ask for a scientist, I asked for an engineer. Till now you haven't talked to a single engineer whose tools you use. I mean, this, that. This year the guy who invented USB got a Padma Shri award from Intel. You still don't know him or her. Come on. Okay, chalo, I will take Nambi Narayan as a half engineer. Anyone else? And these are the people whom you are naming, except Vishwesvaraya, are our generation people. Like we have known him. From history, you can't name a single engineer. And you all are thinking, kabhi to padha hoga kisi ka naam. So what's wrong? You did engineering, you worked hard to get into engineering. You should have written an entrance exam, right? And then you'd have written another entrance exam to get into masters. Name the 4th engineer. Aryabhat. Okay, the USB guy, right? Half. Okay, chalo, I'll give him 1. Again, our generation. What does he or she do? Okay, I must confess I don't know. What, again, does anyone else know this name? So he named Patirappa. Do you people know? Anyone else knows? How many people have heard his or her name? Raise your hand. None. 1. Famous engineer. Satish Dhawan is a scientist. Come on. Let's not abuse our clan. Jack Kilby. Finally somebody come up with a proper engineer's name. What did he do? You don't answer that question. Let's ask other people. What does Kilby do? He got a Nobel Prize, by the way. Very few engineers get Nobel Prizes. He got 1. What did he or she do? Leda. Why are we not famous? I'm not asking the question, name the famous engineer. I'm asking the next question. Why are engineers not famous? And don't get me wrong, engineers have been famous in their lifetimes. If you ever visit Paris, I will ask you to, everyone goes to see one building in Paris, right? Which is Eiffel Tower. On the base of Eiffel Tower, the first floor, on all sides, they have written the names of famous people of their generation. So at one side, you have the scientist, Ampere, Lavoisier, Fourier. The other side, and this is why I like Eiffel Tower, they have named 20 famous engineers of that time. You know what's the worst part? I couldn't understand the name of any one of them. So why don't engineers become famous in history books?
We made very important thing. You're standing in a building. Somebody discovered the idea of how to make a building. Somebody came up with the idea of Portland cement. You're using a mobile phone, communication. Do you think this happened just out of thin air? So I have a theory. I might be wrong. The reason why we are not famous is because we make money. Most of our products make money in our lifetime, and money and famous thing don't have a correlation with one another. Okay? Which brings us to the whole thing, whatever we make has to make money in the market. So it has to have certain specification which the market can understand. Right? And this will become very important when we start picking up the next slides. Because we might come back and say, here is the best camera in the work. Market will still not buy it till you convince it to. There's a quiz which I was going to do in my next lecture, but let's do it now because this is a very important thing. All of you have cameras? Anybody without a camera these days? Yes, no? All of you are just looking at me saying, kya fark padta hai? The world is going to come to an end anyway. Why should I answer this professor's question? All of you have cameras, right? How many megapixels? 38, one number? 48. Ah, okay. So, no, sir, not that low. Huh? I've got a good phone. So 48 megapixel. What other numbers we have? 16 or 60? Sorry? 16, 16 megapixel. 53 megapixel. Well, that's a strange number to have, but okay. Anything? How much? 200 megapixels. Somebody got a phone in his dowry. (200 megapixel). Good. Anything else? 10 megapixel. Fine. And you have looked at, most of your phones would have multiple cameras now, right? Mine is a bit older, so I have 2 here and 1 in front. Some of you have might 4. My prediction is in 10 years, we'll just have cameras in the whole background, right? I have got 40 by 20 arrays of camera on my phone. So all of you are engineers, right? Which brings me to the next question. How many megapixels do you need? So all of you answered this question, how many you have, how much do you need? It's not a dharmic question. It's not a Kumbh Mela question, right? That's a good question. That's a very good question. Because if you ask that question, then you will answer the question, how many do you need? So let's ask the question. Need for what? What do we use our cameras for? And camera is a sensor I'm going to spend a lot of time. I did my PhD in that field, by the way. Okay? So we're going to spend a lot of, we are going to make a camera for heaven's sake. If we are lucky, we'll make an image sensor in Cadence. Okay? So, and this is why I'm asking this important, because I could just tell you, this is the sensitivity we need, this is the intensity we need, this is the frequency of converge rate we need. I don't want to go through that. I want you to raise the question by yourself. This is what we need. So what do we use cameras for? Capturing images. Good. What do you do with those images? Because first I'm going to capture an image, which means I need certain specification of the image, right? Got data, okay. But no, I didn't ask you to. I asked, what do you do with that images? आप क्या करते हैं? Memories. When was the first time you got a phone? In year 8th, right? Give me a year. I'm asking to you. Which year was the first time you got a camera or camera phone? And if anybody thinks the question which I'm asking you is a bit more private, stop me then and there. Okay? Just say that, I got the phone in my dowry, sir. I cannot answer that question because there's Anti-Dowry Act in India. That's perfectly fine, okay? Remember, I come from Arunachal Pradesh, where men have to give dowry to women, okay? So we are equal opportunity abusers of Indian law. So 2008. So 16 years ago, you got a camera phone, right? You got 2016. Let's take the number. 8 years ago, you got a camera phone. So you have been taking pictures from 8 years? You remember the picture which you took on 13th of January 2009? It was Makar Sankranti or Bihu or Ugadi Day. Ugadi 2009 was Pongal Day, right? Yeah? I'm sure you have taken a picture that day. You have no idea. Do you remember where it is? In your phone somewhere it is, right? Or you have transferred the phone to a Google data space somewhere, right? If I ask the same question to any one of you, what have you done with your images? The answer would be nothing. It's stored somewhere. You answer the question right, for memories. We all think this will be in our memory. Now, my father's generation had the 35 millimeter camera phone, right? So one reel will give you 35 pictures. So on their wedding day, they had this exactly 35 photos, and they know which photo has which one in it, right? Or my early childhood. I have 20 photos of my early childhood. Half of them are me looking like because you're not ready for so you could not revise, there was no Photoshop, but you knew exactly what that photo is. You guys have 2,000 photos or 100 photos, at least 20 photos a day. You have no idea about it. Am I wrong? So question still comes, what do you do with the images? So memory is one question I have ridiculed right now, it's not going to work. Maybe when you become 60 or 80 and you go through your stash of 1 million photographs, you at least take one photo a day, right? 365 in a year? More? 500 in a year? You live for at least 40 or 50 years of your camera picture taking. So that's 25,000 photos minimum. And this I'm talking about people who use less phones. If you go to a wedding, 200 goes in a day. Right? Or birthday party, or you reach some nice pictorial places, rather than looking at the lake, you start taking picture of your lake. And then you turn around and take your own picture of the lake. I think you should know I was there. But anyway. So memories are not a right answer. So then again the question comes, what do we do with the images? Have we? Have we extracted any information from our pictures 10 years ago? No, we haven't. Framing a video. I haven't come to video yet, sir. That's my next question. I'm still at still images. I'm coming to video, don't worry. We're not too far. Well done. That's one answer which I have got, which is very correct. You send it to your friends to see. First thing you do, but first thing which you do with an image is look at it yourself. Agreed? Either on a phone or on a computer screen. Yes, no? So an image should be big enough to be displayed on my screen. Now you know what's the next question coming. What's the resolution of your computer's or of your monitor screen here? All of you have got mobile phones, right? What's the resolution? How many pixels does it have? And Babu, your homework for all the boys and girls is whatever electronics you have in your home, you need to know its specifications tomorrow. Or else you will do the 10 push-up routine here as well. Or running in the round, or you'll have to sing a song, one of the options. I don't care if Gian, I don't get another Gian or Spark course ever in my life. And I'm known, as long as I don't abuse certain individuals, my visa will not be cancelled to this country. Okay? So you should know what, and you are electronics people, you are engineers. We should know what we are having. I mean, we know the shirt sizes. Okay, mine keeps on increasing every few years, but we know that. So now do a Google search on your own phone and tell me what's the resolution of your screen. And those of you who are not doing it will get the question from me, don't worry. Phone screen pucha, laptop screen nahi hai. Huh? You do remember I'm the old school professor here. Answer the question which are asked. So you have a mobile phone with you right now. You should be able to figure out its brand by going into settings about, And then you should be able to do a Google search, what's the resolution of my screen? That's a very important question which I'm asking, because we have just realized the first thing we do with an image is we look on the screen. And most of the time we are looking on a computer's mobile phone screen. Sorry? I get a number? 2340 cross 1080. Give me, so do that multiplication. Or else I have to do it on the whiteboard. And these days I'm teaching my young son, so I'm very good in doing 4-digit multiplication. Yes? 9,21,000. 921,000. Good. So one person has 921,000 pixels. Another number? 25,90,000 pixels. So 25 lakh 2.5 megapixels. Right? Another number? How do you have got 25 lakh? What screen have you got? This looks like one of the fancy screens Samsung executives carry. What's the resolution? What's the resolution, X versus Y? So 24 10 to the power 3 into 10. Yeah, okay, yeah, sorry. No. It can't be 25 lakhs, is it? 2.5 megapixel. No, yeah, 25 lakhs, yeah, sorry. I'm counting from mega to lakh. Okay, guys, engineers. Go in 10 to the power X units, okay? Mega kilo, not lakhs and crores. So 2.5 into 10 to the power 6, okay? Right? And I had 971 kilopixels there. So 2.5 megapixel, somebody else said 2.5 megapixels. Madam? Oh, now she has got a good phone, 4.3 megapixel. Well done. Whom did you abuse to get your phone? Was it blackmailing your father to get that? I will not study masters till you give me a fancy phone. Well done. If you can get that, be my guest. And Europe often says, make a girlfriend or boyfriend from humanities department. Their phone or computer will stop working someday. They will bring it to you fixed, and that's how you learn what's the inside of a computer. If you can fix it, the relationship continues. If you can't fix it, it breaks, but at least you have learned about computers. So, very interesting story. 4.3 megapixel is the highest number which I got from a lady, and that was in minority. Most of you have around 2.5 megapixel. And you are taking a picture which is 200 megapixel or 60 megapixel to display on a screen which can only do 4.3 megapixel. Kuch to gadbad hai. Isn't it? So essentially, we are taking a picture which has higher resolution than what we can see. Of course, you will say, but sir, I can zoom in and I could figure out who was the person standing behind me. Okay? But you don't do zoom in most of the times. First question. Second question. So that was a dilemma we have, right? Our screen cannot display the images which we are taking. Good. So fine. Okay, sir, that's not the only screen we work on. We also have computer monitors which are big. What's the resolution of computer monitors? Another Google search. I should not be giving you all the Gian, right? You have Google. You should be able to figure that out by yourself. 1920 across 2048 is one number somebody is throwing at me. 4K is some number thrown at me. Which is 4K? This is not 4K. I should make some of you stand there and look at the specification of this projector. No, we can't do. None of you are tall enough to reach till there. I think the tallest person here has been Muralidhar sir, and I can't make him do any work. So even your computer screens don't have that high resolution. So we found two applications of the images which we take. Either we see them or we send it to somebody on social media. And the social media people are also looking at the image on the same screen, mobile phone or your handheld. So why the hell are you having 200 megapixel? Well, dowry is an answer, don't get me wrong. When you're taking the Dahej, which is highly illegal in this country, higher is the better. Now the reverse question, you also take selfies, right? What's the resolution of this camera, the front camera? 14 megapixel, 5 megapixels is another number which I'm getting. Now things are becoming interesting. 10 megapixel, but this is significantly smaller than our back camera, right? And we do take a large number of selfies. And selfies images are not that bad, is it? When you take your selfie, is the image quality much worse compared to when you take this? Not really. The image quality is worse. If it's 60 megapixel versus 5 meg, it has to be worse. Why don't we see it worse? When you zoom, essentially for your own screen, it doesn't matter. And now all of you are going home. Next phone, 5 megapixel back camera. So why do we have 50 megapixels? None of you are professional photographers. Is anybody who's a professional photographer here? I'm a semi-professional, but I would be the closest to which comes to this. So why are we having 50 megapixels? You don't even have a good lens. You don't have space to make good lens. As you know, electronics engineers move very fast. We keep on making more pixels. Our colleagues in physics department, whom we gave the task to make lens, they are slow movers, right? Every 200 years, one major discovery. So Apple fell down, nothing has fallen since that time. So why do we have 50 megapixels? Do you? Do you capture more information is the question which I am asking. You can capture, I agree. But actually to capture more information, you would need a good lens. Have you seen those sports cameras with massive lenses? They capture a huge information, right? They have got a good lens assembly. We don't have good lens assembly. We can't have. We're not going to have a phone which is this big. It's not happening, right? It will not fit my trousers. So why do we have 50 megapixel? Well, I used to give my second lecture, it used to be, when will we get a gazillion megapixel? You know, more and more is better. I'll give you the answer to it right now. We have that many for a very simple reason. It's called the market. Most of my customers have no idea about image quality, lens resolution, illumination intensity, all these technical terms. Hey, most of my engineering students have no idea about it. Had I asked you what's the quantum efficiency of your pixel, you'd be like, what the hell is quantum efficiency? Agreed? The only specification you know of your camera is number of pixels. And that's the only reason I asked you that. Fill factor of your pixels? Range of intensities it can capture? Nah. But you do know I have got 200 megapixel, which is more than 50 megapixel. So market decided, and because exactly if I ask you how many megapixels do you need, you'll only need 3.2 megapixel. Because the worst thing which you do with an image is not to look on your screen. 2.5 megapixel is what we figured out was the average screen. The worst thing which you do is print. That's where you need dots per inches. Remember, the printed image is bigger. And the largest you will ever print will be that postcard size or an A4 size. These days you don't even print that many. Now that process is abusive to image. It needs more what we call as dots per inches, DPI. So there you need more pixels. So if that's the worst you are going to do with your image, 3.2 is good enough. And this is why we had a generation of digital cameras with 3.2 megapixel or 5 megapixel is good enough for this thing. And this is why your front cameras are very much static at 5 megapixel range. For things which you are going to do, that's good enough. We still sell 50 megapixels to our customer. So what technology can say this is good enough for you? I mean, we need only 6 shirts, right? Maximum. 1 for each day on Sunday for washing. So I ask my boys, how many shirts do you have? The person with the red shirt. 5. Oh, there's a gentleman in the room. I shouldn't even ask this question to my female students, right? I'll be killed. And of course, I should never ask this question to my wife. That will be the end of civilization. Particularly when we are in India to also attend a couple of weddings. And if that's the season, then that question should never be asked. So we're talking about the specifications of our sensor. We are going to find all specifications of the sensor in exactly the same way we did it. So first specification we talked about is resolution, the number of pixels we need. Okay? So one thing is technical needs, other thing is a marketing need. So market decided that my customers are happy to pay for a better phone, or let me correct it. My customers are happy to pay for a camera with more megapixels because that's what they think is better. X is, I mean, all of us learned number system in a school. 100 is better than 50. So they're willing to pay for it. If they're willing to pay for it, hell, we will sell poison to our customers. We are engineers. We do sell poison to our customers, right? Don't we? One person is saying, yes, sir. Poison, nicely graded, made in, Intel labeled poison would be good enough. Okay, let's ask an ethical question because we're also going to do a lot of AI in next 4 days. So let's think, this is an example which I'm not taking from my work. I'm taking from another famous person, but I kind of hope you have not heard of this example. So let's think I make a product, okay, which everybody in the world will have to use, will use it. You'll bring it to a market, right? Let's put a substitute. It will kill 20,000 people every year. Now, will you bring that product to market? Yes or no? I just need yes or no answer. So the question is this. I make a new product which everybody in the world will use. You cannot not use this product unless you live in Forest of Andaman or a rare place. You have to use this product. Okay? So everybody is going to be a customer. I can be a billionaire or a trillionaire. But the product will kill 20,000, at least 20,000, if not 200,000 people every year. So all those who will still bring the product in market, raise your hand. 1, 2 persons. All those who will never bring the product in your market, raise your hand. All the girls? No, we are not going to kill the people. And the people in the back are, when is lunch starting, right? Or you are like, sir, as long as the package is good in that company, will bring the product. Right? Campus placement hona chahiye. But majority still said they will not bring the product to the market. Let me give you an saying that this product exists in the market. Have you heard of something called automobiles? Cars, buses, trains, planes? Everyone uses them? Just by sheer accident, they killed that many people. I mean, 20,000 would be the Indian number. Global number would be much higher. And then they cause pollution and everything. That I'm not even talking about pollution, yes. So I should have gone for 150,000 number. And maybe that would have made even those 2 people who were willing to kill 20,000 people turn their hearts. Now, this may not be our problem as engineers, because we never think about the end goals of our product. I mean, heck, we are not even thinking what will happen to this mobile phone 5 years down the line. All of you are buying one every 3 years, 4 years? Or Apple and Google forces you to buy a new one because the software update does not work? What happens to these when you give up? They go in landfill somewhere. For all the talk of recycling, we do not recycle a large majority of our electronics. So it goes in landfill somewhere. Only for an alien civilization to come on Earth 1 billion years from now and look, oh look, these were 2-dimensional people. They had everything in 2 dimensions. We don't think about these things, particularly when it comes to electronics. But as we are collecting more and more data and sensors, we need to start thinking about these things. Not that we can do anything, let's be honest. If our immediate market gives us money, we will still take it. You know, the company which paid highest in my campus placement was a company called, what does it do? What does ITC do? Tobacco, makes cigarettes. And you all were happy to take a job in it. Paid the highest. So we have got that marketing dilemma to be worried about as well. Good. So we decided on megapixels. Our next problem is this. We can only do 2D chips. So everything has to be in 2 dimension. Rest, these are research topics. We can have 3D stacked chips. The only 3D stacked chips which are in market very successfully are the memory, because they are same kind of chips. You have one memory, another memory, and you can stack them all. Different type of chips coming together has been very tricky. Research-wise, yes, but it's very tricky to make in market. So most of the stuff which is in the market is a 2D chip. So everything has to sit next to one another. Now the human brain doesn't do that. I mean, do you know what's inside in human ear? It has layers of canals, small bones, big bones. In the human eye, we have lens, we have aqueous filter, the liquid, then there's a retina. Behind that retina, you have different cells, and then you have got a rope wire going in. So the nature had the 3D advantage. We don't. So we have to do everything in 2D. Good. I'm already coming to 12:16. I was hoping to break it shortly. So let's see what we will do in the next few days. We will be learning, well, as I said, there is no necessary a book to give to you to learn. I hope I will be able to write that good book when I get some time and rest. So learning primarily from papers. This is more of a thing you use IEEE Explore for getting papers. Most of you would have free access to it. Most of you still end up using Google or Google Scholar. Not the best source of knowledge. Generally speaking, Google is not the best source of knowledge, but one of the reasons why I figured out Google Scholar is not a good source of knowledge is one of my own papers was heavily plagiarized by somebody. They changed everything except the list of authors. So they took the entire paper of ours, changed the name of authors. So my name disappeared and all of my colleagues' names disappeared, and their name came in there. So mine was a paper in IEEE Transaction. This paper was in some international journal of singing and dancing. Google somehow figured out that was more important than my paper. So when you search for that topic, it comes before the original freaking paper. And this is why it's the only half decent good source of knowledge. Okay? Now most of you would have started reading papers. We'll be giving you loads of papers to read, and you'll have a day to read and come back the same day. We'll also see if we can do a mini project here. So the mini project challenge this time would be to make the best pixel possible. I will teach you how to design a pixel, and when you are in the laboratory, we will try to make it as small as possible. The smaller the pixel, more megapixel you can keep it in phone. Not because of technology, because of the market. Okay? Good. This next brings us to the next question. Most of you who are doing PhD and masters would have had the unfortunate realities of reading a paper, and you would have read a whole paper, spent an afternoon only to figure out it was completely useless. Some of those who are smiling have gone through this experience. Those who are not smiling are like, this guy is useless. If the paper has been peer reviewed, it should be highly useful, right? So this is my way of reading a research paper. I'm telling right in the beginning so that when we do this, you can understand, and do the same with my papers. Read the introduction. See if it makes sense. If it makes sense, don't read the next section. Go straight to the conclusion. See if it still makes sense. These two make sense, then possibly you can read the next section of the paper. If your introduction doesn't make sense, look at the references cited in the introduction and see if they make better sense than this paper. Okay. And if they don't make better sense, then life is not worth exploring this further. Stop reading it. Because you can spend the whole evening and you'll still not be able to do this thing. Then after introduction and conclusion has made sense, go to the next section, which is generally the theoretical background. And this is where you will have loads of equations. Now let's be honest, as engineers we don't like equations. We all thought we were good in maths because entrance exam likhe the, right? And we know the limits of any calculus operation immediately. We remembered all those NEET and what's the exam called? Is this called NEET these days or JEE or what's the fancy name? JEE, right? So because you have written the entrance examinations, you know you are good in maths. Let's be honest, you are not. Okay? We know how to solve a mathematical problem. We don't appreciate maths as much in our schooling system. And same with physics. So my trick is, do not read that theoretical background section. Read the methodology and experimentation section, because here you will understand a bit of what has been done and what is the result of it. I skip all the maths in the first time I'm reading a paper. Okay? You can come back. If everything else makes sense, come back to the maths and then try to ascertain maths. Because somehow we have this magical understanding within ourselves. If we can write an equation to look very complex, we are good scientists. And what is a scientist who doesn't give a complex equation? I mean, Einstein was hopeless. He only gave E is equal to mc square. What's the equation with 3 terms? Agreed? So those of you who had the misfortune of reading research papers, you would have seen fancy looking long equation. Can anybody tell me what does that equation do? And this is from a meme which ran around when I was a PhD student. All of you in JEE exam, how much money did you guys give to get in? See, that's the kind of abuse I used to get. And now you guys are not even finding it funny. So Muralidhar sir, you are going to get 5 complaints from this batch. So you are going to be in trouble, not me. All the maths are wondering. Yes. Do you think both sides are 0? 2 is, so this side is 2. Somebody did the limit. Said you were the JEE exam preparation, right? That limit I will know it's equals to 2. What's on the left hand side? Sin square x plus cos square x is 1. What's that log limit? So this side is 2, that is 1, so that has to be 1, right? So the equation basically says you 1 plus 1 is equal to 2. Looks really cool. Unfortunately, in science world, we do end up doing these mistakes. And it's not a mistake, it's just we understand this equation by ourselves because we have spent a lot of time developing that equation. And we forget that our end user does not have that much time to understand that equation. He or she only sees that equation for a second or 2. And most of us who are not mathematically well trained, some of us are, don't get me wrong, there are some engineers who are very good in maths. The good majority of us, we are good in solving problems. So you will see such equations appearing quite frequently in research literature, even if it's top journals. And hands-on, I have also done this. Some of my papers will have fancy equations which I can explain in much better fashion. So that's why I ignore all the maths in the beginning. Okay? In generally speaking, for use IEEE for electrical engineering, ACM for more computer background, most computer science colleagues will also put their AI-based papers on archive. Try to read full journal papers. In electrical engineering, we also publish conference papers, which are the smaller versions, and generally they don't contain all of it. But mind you, the word proceedings of IEEE is not a conference, it's a full journal. That's the most important one. But proceedings of IEEE conference on XYZ, that may not be carrying everything which you need. Maybe still be a very good paper. And there are some decent science journals like Science and Nature, which has occasionally papers published from our community. They're primarily linked to biology. Look, I mean, a brand new phone is not as interesting as found the bacteria which is going to kill all of us. So the bacteria which is going to kill all of us gets published in Nature, brand new phone, well, we make money. Okay. So this is what we are going to do. We are also going to do a bit of artificial intelligence. I will at least spend a day on, not on neural networks as a whole. That will be a different course taught in a different department, but how to make these. Because I said we are going to make head. So in head, we are going to do the sensor design. We're also going to do the hardware design of the neural network, the brain. We still don't know how the brain works. Because if we knew, we would have made one. I sat in a very interesting talk on, I was working on psychophysics. There has been few faux pas I have done as a researcher. We all do, right? Early researcher, we are bright with our energy. So I was working on cameras. And of course, I thought, human eye is a good camera. So if I go to a biology department and understand how the human eye works, I'll come back and make the best camera in the world. So I took a year break in my PhD. I got a scholarship to go to any institute in Europe. So I went up in Max Planck Institute of Brain Research. So, you know, how long biology can be? I mean, we always thought we are better than people who are preparing for medical entrance exam. Let's be honest, engineers are better than everyone else, right? Everyone is a yes, yes, yes. That's a good line we all can agree to. So how hard can it be? And people who study the human eye as psychologists, medical doctors, it can't be that hard. I went for 1 year fellowship to study human eye. First 3 months, I realized these guys who have been working on human eye for 200 years don't even know how this signal converts from light to the electrical signal here. Forget about what's happening in the brain. We still do not have pure understanding of how this how a billion pixel goes into 11,000 signals is an unknown thing for us. So mimicking the human brain is tricky. Mimicking the human eye is also tricky. The other interesting thing which happened was there was a guy from IBM. IBM used to have a big project called, I think it was called Deep Blue. They were making a big, powerful machine which will mimic the human brain. And this gentleman who came and talked to us about the memory stack structure of this big machine. They were talking about DRAMs. And the idea was like we are going to mimic the human brain memory. A very senior psychology professor who has worked his entire life on human memory raised his hand and said this thing. Ah, you have figured out how the memory works. Shit, 40 years of my research gone down the hill. Please take over my professorship. I am going to retirement. What's the use of working on human memory anymore? So thing remains, we do not understand. What we do know is what does it do? We don't know how does it do. So if we can somehow get similar information or similar result as the human brain do, we will be happy. Things, we know it looks at, if we look at this image. So do you know what I'm looking while I'm looking at you guys? What my brain keeps on going to? There's a gentleman who's flicking his pen. Nothing wrong with it, continue working on it. But that's a motion. So rest of all you are still, like, you know, a cobra snake waiting to bite me. So things which are still does not enter our brain immediately. Things which are moving cause immediate action. Okay, do this experiment. Let's do it. So look straight to me. Raise your hand on one side. And then don't worry, I'm not going to make you do RSS salute or Hitler salute for that matter. Just move it sideways. And you will see as it starts, this way, this motion. As it starts coming favor. So here, I don't see this motion happening as well. Here, I don't see my hand, but I feel something is moving. And as I go forward, I of course see things. So our lateral vision, so we have got two. We have got a central vision system where I can see everything. Sideways, I only see motion. I do not see exactly what's happening. To some reason, I see that we grew up in the forest. And I believe in theory of evolution. I don't know where your religious background right now. But let's assume it to be correct. Well, it is a theory, so it has to be correct. When we're evolving in a forest, we have to be worried about moving things. Moving things are bad. Snake moves, lion moves, tiger moves. Still things, not so bad. So our eyes or brain trained to look at motion first, and then it's let's see what is. So we know we can see motion very quickly. So as something which you would like to do in our imaging system also is to look at motion. Something has happened, or sound, something has changed. So if I speak in monotonous voice, the same sound, that's the quickest way to put you to sleep. I can still put you to sleep. Professors have got this unique ability of mothers singing lullaby and professors teaching a lecture. These are the two things which put people quickest to sleep, right? So the reason why it does it, we get a constant same frequency, same tone. So unless you go up and down, take pauses or do things, life becomes tricky. The other thing is that we only have a constant span of time. So how long can you concentrate on something for? And I'm waiting for somebody who will say, I do pranayam every day in the morning and I can concentrate for 2 hours. 5 seconds. That's a classic master student, isn't it? 5 seconds and see which other job campus company is coming this time. So there is a thumb rule which says the number of minutes we can concentrate is equal to our number of years we have lived. And it saturates at around 22, 23. So as we grow up, a 2-year child has a 2-minute concentration span. A 3-year child has 3, and so on and so forth. Around 22, 23, we saturate and we stay till there for the rest of our lives, slowly growing or increasing. And after a while, of course, we start falling down. So you cannot concentrate on a lecture for more than 22 minutes, even if you are assuming you are terribly good students. So one of the reasons which you would have seen every few seconds I break the speed of lecturing. I go and talk about something more silly, which is often more fun than engineering. So we need to find something which at least works for 22 minutes non-stop. Okay? And this raises the next question. So if we get time, I will talk about history of engineering someday. If we get time and we get bored of sensing. I'm also thinking of writing a book on history of humanity. And engineers should never write history books because we hated history in our school. Agreed? There are few things we all engineers can agree on. History was, and I'm kind of hoping no historian will ever see the recorded lecture of a Gian course. The first 5 minutes would have bored him or her to death. The reason why we don't like history is because it teaches about wars, kings, queens, which year what happened, who gives a damn to what year what happened. I think that's the wrong way of looking at history. And as an engineer, of course, I will say historians don't know what the hell they are talking about. We, of course, know better than that. But the way I look at history is, history of humanity is actually history of engineering. At this point, you might think I love my own field too much. But if we get time, I'll prove it to you. That kings, queens, battles, they are always very local. If you're looking at globally, the important epochs in our history were things like invention of wheel, invention of fire, the ability to throw a thing, a turnpike upwards, ability to make guns quickly. These are the things which were epochs of our history. So I'm looking at history from an engineering perspective. And if I get time, we will do that as well. But for the time being, let's do a history of AI in one slide. So my take on AI is humans started thinking many, many years ago. And then we thought, can somebody else do our job? The job which frightened us the most was multiplication. addition, subtraction, multiplication, division. And that's why we came up with different computing machines, starting with abacus all the way till computer. Same with communications, right? We are essentially asking the machine to do our job. And now we are thinking, can somebody else do the thinking for us? And that's the artificial intelligence for you. We'll stop for the first part of the lecture. It has been an hour of talking. I will take a break every hour because you can't concentrate for 22 minutes. I can't talk for more than 20 an hour, and I forgot to bring my water bottle. I did have my water bottle somewhere, but I dropped it somewhere else. Okay? So, are there any questions on what we are going to do? At this point, you might say, sir, you taught absolutely nothing. How the hell we will have question on absolutely nothing? Yeah. Somebody has a question on absolutely nothing. Well done. Amplify your voice. I can't hear. Yes. Oh, thank you, sir. Of course it is different. They're two different things. I said you need 3.2 megapixel for printing. For printing on a postcard size picture, if you look at how many pixels are needed to fool the human eye. Look, we print as dots. Okay? If we print A, we just make dots of A. So if you really magnify it, there is gap between these dots. So to fool the human eye, we need that many megapixels. In the same way, to fool the human eye when it comes to video, I said I will come to video at some point of time. How many frames do we need per second? 24, even 20 is enough for most human beings. Right? So if you take 20 still images, it fools the human being. But that's not the whole, I mean, we are missing motion in between the scenes. There are applications where we make 100,000 frames per second camera. If you're looking at high-speed chemical reactions, or if you're looking at something moving very fast. Okay. Most of these are export-controlled cameras because they go on special things. But you are losing information there. So what I meant to say was, if you're printing, that will fool the human eye in thinking that it's a continuous image. If you keep on zooming it, of course, there'll be a difference in resolution, but not on your screen. If on your screen the image quality is different, there's more to a camera than just resolution. And the more part will be, intajar kijiye, the movie is still coming. There are things like how do we, because essentially we are converting light to a voltage. How are we converting there? What's our noise limit? All the other electrical things which we hate will come in picture. Signal amplification, noise filtering, data conversion, ADC, DACs. Okay? So all of this leads to say how good the image quality is. Which is also as saying megapixel alone were not enough. Does our customer know about that? Well, you guys don't know about this, and you are electrical engineering masters or electronics engineers masters. Okay? There was a time when one of the Taiwanese company, they cut down on the image number of pixels, and still their image quality improved. But market didn't like it. Okay? Any other questions? So you have had an hour of multiple speeches about how cool this place is. An hour of me talking about how everything else is hopeless. In the second half, we will start looking at the first sensor which we are going to play with. The sensor which we are going to spend most time would be the cameras or image sensors, as we call them. We don't use the words cameras, we use image sensors here. Not because they are, well, they are the coolest. I did my PhD on them, and my chair is called Chair of Image Sensors. Because they are also one of the most successful in market of all other cam sensing technology. And there is the audio sensors as well, but they haven't changed dramatically. And do people still use landline phones? No? But those who use, I mean, okay, think of it this way. The sound quality in normal mobile phone calls can still become very bad. But image quality we have learned to improve if we have decent resolution. So because these sensors have been fairly market successful, they are fairly mature as well. And they were the first to integrate. They're also the first sensor we started working on as humans. What's the first thing we did as humans? What's the background? We used to paint things on caves. So it's our natural tendency to record our own history. That's why we take pictures. It's not that we like ourselves. Okay, most of us like ourselves as well. But think of it this way, taking your own picture versus taking picture of Rajnikant, whose will you take? Oh, sorry, it's Andhra, right? So Nagarjuna, or who is the superhero these days? Who is the you and old guys don't watch Telugu movies anymore? Pawan Kalyan. Okay, this is later to my generation. Do they still do the, how many of you are from Warangal, from this institution? Do they still do movie nights here, or they have forgotten that thing? And you still have to watch a Telugu movie every third week? Sorry? So in our generation, we used to have Hindi followed by English followed by Telugu. And that was the ragging I used to do to my students. They had to translate the Telugu movie live to me. And trust me, it's a heavy ragging because, let's be honest, most Telugu movies have romantic scenes in them. Ask a 17-year-old to translate that in English. Brilliant. So what's the law of ragging? When can you be punished? After you have done the ragging? So 25 years down, maybe I will not go to jail anymore. So bottom line remains, we like taking our own pictures, irrespective of how good we look. We like recording our own history, either through, and most of it in the past was through images. We started painting things. So I'll go through images of, most of us think things like selfie is a modern innovation. We have been making self-portraits throughout the history of humanity. Most painters who are famous also painted themselves somewhere. So we'll go through this in the second half. It's 12:42, I will call a break now, unless there are any other questions on what to do. How many of you have used the software Cadence before? One person, which means he can teach the rest of you, right? Okay, then I will do an introductory session on Cadence before moving. So if you want to do a camera pixel, camera chip, we would like to do on work on Cadence. And then I will have to go and figure out how many of you are actually registered here and how many of you are here just listening to me talking about everything else. Okay, thank you very much. We'll see you at what time, sir? What time after lunch we meet? 2:30? Meet at 2:30? Okay. Good. It's Saturday today, isn't it? So ideal electronics professor teaches on Saturdays and Sundays. See you around. Give that as a challenge to the students. Whoever gets it working gets the first prize. Okay, I will try. The more loudly I speak, the more tired I become, which means less I can teach.
So if you have any portable mic, you can use it.
My laptop has a microphone. We should do the mic problem. You guys can hear me there, right? If I shout loudly, they will just hear noise. Da, 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 da. Conference hall has the portable mic. Did you go to the conference hall? Give it another 10 minutes, if not.
My specialization in electronic instrumentation and embedded systems. I am in second year and currently I am doing internship in AMD Hyderabad.
You're doing internship with
AMD Hyderabad.
AMD Hyderabad. Then you should know how to do chip design, right? Good.
Hello, I'm Sharad Soni and I'm pursuing the same degree as in electronic instrumentation and embedded system. I'm from this department. And I'm doing an internship in Honeywell.
Okay.
Honeywell.
Honeywell. Okay.
Yeah, in the aerospace department of Honeywell, not the automation.
So this is why we kept an aeroplane at the entrance of the institute. People like you.
That I don't know. My profile is in embedded.
Playing it here. So everyone should listen your sound. Go on. What's your next specialization? This. IIT route. There is a IIT in every district. So is there a JNTU in every district also?
Yes. I never started that. I'm finally uploaded to
Okay, good. Kakatiya, so you're from my university. My degree is from Kakatiya University, so I'm Kakatiya University alumnus. Okay. Under who? Under Prithvi ma'am, okay. She was in new faculty when I was a student. Okay. Okay. That's her introduction. You know my PhD supervisors, you should know me. Good, good, good. Have you missed anyone? Yeah. Are you still part of our course? You're not part of our course. If you're not part of our course, you can get lost. Okay, okay. Can you hear me now or not hear me?
Yeah, little bit, sir.
Yeah, you might like to get one of, what is the first application of transistors? First commercial application. Audio amplifiers. That's why all the textbooks, they start with designing an audio amplifier. If you look at Milman, MKS, or any other classical textbook, they design audio amplifiers. And many of the students keep on imagining, who designs audio amplifiers? Wow. Okay. So in today's lecture, the reason why we are here is at some point of time, I would like you guys to do a hands-on work on designing a pixel. We'll design one pixel. Okay? Now, one pixel is not that big a thing. On paper, it doesn't look that big a thing. You have got 100 megapixels. Yes, most of the time, a megapixel array is just a tiling of the same structure time and again. So if you can do one pixel properly, going up from there to few megapixels is not that impossible. Going beyond that, it brings other issues related to wireline issues and other things. The other reason you in batch is fairly interesting is you have got a healthy mix of people all the way from robotics to digital communication to embedded systems. And this is what modern chip design is becoming. Classical chip designers were very nice people. We dealt about circuits, we did the bipolar circuits, MOSFET circuits, and we are happy. But modern chip design is no more that. So take for an example, the signal. If you're making a signal move at a few gigaspeed samples per second, and let's take our 10 megapixel camera. Okay? So 10 megapixel camera, each pixel we convert it to and digital in 8 bits. So I already have got 80 mega samples. Okay? And then I take 20 frames per second. We are already at, so 80 mega samples in 1 second, I take 20 samples. How much data am I producing? So one frame is 80. I have 20 frames per second. So in 1 second, how much do I produce? to 20, which is 1.6 gigasample per second. Despite the fact it's only a 10 megapixel camera, my output is 1.6 gigasample per second. So if I move that much data out of the chip, it does not come out as a voltage signal. It's very difficult to take it out because you now still need to start wondering of it as if it's a communication channel. It's no more a voltage line. Every wire becomes a communication channel. So you have to start looking at reflection. You're sending a transmission, you'll have reflection from the line, you'll be forming eye diagrams, and all those things come into picture. On one hand, it becomes a communication system problem. We are going to look at sensors, where we're dealing with things, none of which are electrical. Sign, sound, vision, smell, taste, none of these are electrical signals. But our entire chip design, the entire electronics design is dealing with electrical signals. Good? So we're going to convert things which are not ours into domain which are ours. So we're going to deal with things which we don't like. Let's be honest, none of us love mechanics in our intermediate. We did mechanics or thermodynamics, is always painful. So we don't like these things, but we have to deal with it. Okay? So first bit of history, and very soon we'll jump from history to a simple pixel design. It's going to be a fairly simple circuit to start with, but as you know, life rarely is that simple. It's good to start with simple things and then see how we do. Okay? This exercise we have already done in the morning, right? And you all agreed to 3.2 megapixel number from me without asking the question, show me how. Never do that. Well, of course, except if you're talking to a professor in Germany. In Germany, you never question a professor. Our rank stands next to God, professor, everyone else. Okay? So, let's do the calculation. So, a postcard is 6 inch by 4 inch. And at 300 dots per inch is a fairly good metric. So, if you go from there, 6 into 4 is 24, 24 into 3, you get around these many megapixels. And A5 will be 8 by 6, and you get around 3.2 megapixels from there. And A4 you can get around 5 megapixels if you're printing it. Now that was the design which we wanted. I told you about market in the morning, but initially when we started, we wanted these many megapixels. The question now is, first was how many do we need? Second is what are we comparing it against? When we started, we didn't have another camera to compare it against. But there is a camera which nature provides, which is the human eye. So we can certainly compare our camera to the human eye. So is your camera better or as good as the human eye? You both have your eyes, all of you?
Yes.
I think there are people whose eyes don't work. And there are many of you who are hardworking people who have got glasses. I've also got glasses now but to read, so I've stopped reading. So one way is to either wear glasses or not read. So we have eyes, we know what we are capturing. We have also taken pictures from your camera, so you know what you are capturing. Both images you can compare. So now tell me how are the performance of your camera versus eye.
Camera is much worse than our eyes.
Camera is much?
Worse than our eyes. That's why.
He's already said we are going to give God 1 point, right? So it's one person much better. Now, this is a very strange phrase in engineering. When we say something is good or better, we use numbers. And this is why the resolution race was fought, because 5 was considered better than 4. So let's start with some more numbers. And let's compare how. So I've taken a fairly, this is a slightly older slide. I took a Canon 5DS, which was a DSLR image sensor. That had roughly 50 megapixel, and the area of the sensor was 860 millimeters square. So it's a fairly large sensor. Let's compare that to the human eye. Okay? So human eye generally roughly has 100 megapixels, but it does not do all the pixels same. You know, in terms of your cameras, you would have red color pixels, green color pixels, and blue color pixels. You will have double the green color pixels than red and blue. We will see why it comes there. So each pixel only takes one light stream, and then we somehow convert it to become a color image. But every pixel does one of these 3 colors. The human eye doesn't do that. It only has 5 million megapixels or million pixels which do color. And then 100 million who do purely black and white. They just measure intensity. So good, let's see who's wearing most colorful dress today. Because we have to do an experiment. So one person wearing red color, could you please stand up? Don't wait for me to make fool of you. Not now at least. Who else? We've got one yellow. Rest all are not boring. Is it yellow? It is kind of yellow, right? So if you could stand up as well. It's all only white and black people. There's another yellow here, slightly different shade. Is there any other color? That should be the exercise. You come to an image sense. So let's do an experiment. So you all can see these three colors. Is anyone wearing blue? Green, blue. There's a lady wearing green here. Could you please stand up as well? Now, can somebody switch off the lights in this room? All the lights, even those lights. All those we can't access? Oh, it's still this light. Projector, how do you switch on the projector? Okay, why don't you guys move to the back of the room? Let's see if we can still see the color of your shirt. So look at that lady who's wearing green. She is becoming black very quickly. Agreed? So she has turned into a black color. These guys are except for one line, everything else is gone, right? The red color person also looks fairly black from me here. Is that the case? Or you guys can see him. Do yellow people still look yellowish for me? And if you still are confused, come closer to me and then you can see the change in color. I can still see a person, I can still see that there is a t-shirt. Okay. For those who are wearing that color, maybe the green color lady, if you can come in this corner. Oh, nice, I should stand here. Yes. So I can see her under green here. What do you guys see her color now? Black. Right? But you can still see her. You can still see her outline, you can kind of recognize as well. And that shows something very interesting. Now your rods are working, your cones have failed. So you can see black and white, you can't discriminate the color. You can see yellow still fairly nicely. So there's a reason I brought the yellow people. Nothing to do with our haldi, but yellow is a very interesting color with black background. That's where our contrast is quite good. Okay? Let's switch on the lights again. Thank you very much, guys. Sorry for being experimental. So we have got. Now, if I take you to the camera which red, blue, and green pixel, I would have gone black much quicker. The green would have gone black, red, yellow. Oh, sorry. Is your blind application taking time? So the other thing which you would have noticed when you switched on the light, some of your eyes might have taken time to adapt. You didn't go immediately to the light. So because you're going to do with light, you're going to do many such experiments. Don't worry, that's not only the first one when some people are standing. You will be doing. One of my students had to do somersault in parks while doing experiments. We're not going to do that today. Good. Another thing interesting is our cameras mostly are straight. The sensor is also a two-dimensional sensor. The human retina is curved. So if you can follow, we have got a lens here, and all of this becomes the place where light is being captured, which is different to our design of lens followed by a fixed scanner. The advantage of doing that for human retina is that it can do a very simple lens. Now, lens is very simple. Whereas if you have seen your physics experiments or cameras, you often have, to get good image quality, you need a good lens, multiple lenses, and a complex lens structure. So we can do with a simple lens structure, but we bend the sensor. Now sensor is straight. Okay. So already we are seeing differences between human eye and the digital camera. We have not yet come to which one is better. That's an open question yet. So let's compare these. Kind of older slide again, this is from my doctoral when we're comparing. So let's see What's the difference between these two and who is winning what race? Not only human eye takes a picture, it also starts doing early processing. Not everything happens in our brain. Things like motion, we don't have time to figure out that something is happening. Something might be coming to kill me. Tell the brain immediately. Some of this happens straightforward at this time of human eye. We will do some more experiments by darkening the room a bit later when I can check all of your eyes to see how good or bad you guys are. Okay? The digital camera doesn't do anything with the picture. All it does is buffers and then sends it to storage. There is no information extraction whatsoever. Right? That's one of the first issues. We already looked at number of pixels. And I've already said number of pixels is kind of strange ratio to look at, but it's not still a good unit to look at. Right, all of you have got your cameras, right? Let's take them out, use them. Take a picture of the light which is up there, just the bright light. So all of you have got a bright light above you. Straight, you can even make your camera vertical and see how. So what do you get? That's going to prove how many of you have got HDR cameras. And now compare the picture you have taken with what you see by your naked eye. So light in dark background, many of your cameras will have saturation. Right? It's just a spot in there. So when you see with naked eye, not only you can see the light, you can also see the frame behind that. Agreed? Who has got clear image? I mean, I'm not going to compare your cameras with us. But you could, one person has got a clear image. Show it to me. But look at that. So he claims he has got a clear image. We can see the light. Can you see the background? Look up. Can you see the background? Look up with your own eyes. Can you see the background? So one person has got, okay. That's a decent camera. Very good. So that's just got HDR abilities. Great. So there are some cameras which will have, and this is actually a typical example. You know what? You should be taking this picture. You take this one and then let's see how good yours is. Yes, so many times what you will see, you will get two blobs. All the white light has become the same. The person is still proud. Good, well done. Now, that comes to a metric called dynamic range. So background is dark, front we have got very high illumination. There's a big range of intensities between background and foreground. The human eye is very good in capturing that. Sometimes it takes us time. When we go out from a dark room to bright sunshine, it takes time to adapt. But we do adapt. Cameras don't take time to adapt, but they have a finite lowest range and a finite brightest range. If it is between this range, they will take a good picture. Above or below, you need a high dynamic range capability. So eyes are much better in high dynamic range scenes. The lady who was working very nice with, you were working very nice with your phone, right?
Actually, where I'm taking, it's not clear. It is processing.
That's cheating.
Software issue.
Software processing is cheating at this stage.
Because of the software.
No, it's still cheating at this stage. That's not a raw image. Try to dark image below you. When you have got dark, you can see if it performs the same in dark. So some cameras perform very, very bright. They're tuned to slightly brighter scenes. When you go in dark, it again starts doing processing again, or the dark performance is slightly inferior compared to bright performance. Nice. Somebody is selling a phone, don't even tell us which brand it is. Okay, so there's a dynamic range difference between human eye and our cameras. One camera performs better, but we'll come to it why it performs better. Then is the power requirement. How much power does your So you charge your mobile phone. Okay. None of you have got SLR camera anymore, so most cameras used are on mobile phones. Okay. And how much power will you give to your mobile phone?
Minimum 5 watts.
5 watts. So a whole charge cycle, it only charges with 5 watts. Do you have your charger with you? Have your charger and look at what's the current going in. What's the current output? What's the voltage and current output of your charger?
25 watts, 63 watts, 65 watts.
5 volt, 10 ampere, 2 ampere. So it's 10 watt, which is coming out from here. Right? How much time is that? How much time does it take for you to charge your phone? Is it exactly 1 second? You connect and it gets charged. No. So it takes time. So now when you next time you charge your phone, you can figure out how much power you are giving to your phone. But generally it will be dependent on your battery capacity. So battery capacity will be 33 milliampere hour or 6,000 milliampere or 5,000 milliampere depending on what batteries you have. Good. Somebody says sir. So you guys can call me Professor or Bhaskar. Sir seems a very strange word to me in German. In German you don't in your phone. Be loud. Display. Well done.
And process.
No. Compared to display. Well, unless you're playing high-speed games and you have got 2 GPUs on your phone, who knows? The display takes a lot of energy. So we are converting low voltage electrical signal to bright light, which you can see. And our end customers are really bad. They can't see low light. Right? We could have shown 1 photon each, but humans are such a silly people. They need to see bright colors and all those things. Now, so that is the amount of power which our mobile phone takes, which doesn't do many of the other things which are human. But now tell me, how much power did you give to your body? And then from there we'll try to estimate how much power you give to your human eye. That's a hard question. It's not a very hard question. You ate something in the afternoon, right? Let's make a list of what you ate and add what's the kilocalorie intent of each one of this. Many of those who try to lose body weight, they do their calorie counting. Right? So,
1500 to 2000 kilocalories.
Yeah, so that's in kilocalorie unit. Here we are talking in watt. So let's convert these two and see how much energy did our eyes need. And remember one thing, my eyes are 24, well, at least for 12 hours, they're constantly taking pictures. Okay? And at least they're taking 20 pictures because I can see video. Well, so first and foremost, let's just compute how much energy was there in our food. And remember, not all of that goes to my eyes and a lot of it is excreted out of the body. So somebody said 2000 kilocalorie you ate. How much is that in units which we understand? Never thought I'm going to do this experiment, right? Maybe we should make a chart of the amount of food which everybody eats. Come on guys, you have mobile phones, do a search. 2000 calories in watt or something else. When it comes to finding the quickest route to Hyderabad, you click on your Google phone, right? How much? 97. What is the number which I am getting? And with that, you are also walking, which takes a lot of energy. So the bottom line is that the human eye consumes a lot less power than a digital camera does for non-stop continuous operation. If you want to have fun, take your mobile phone and take a video. See how long does your phone last. Yes.
So Sir, conversion is like that. 2000 kilocalories converts into 8.3 kilojoule, and that could be said as 465 mAh. 465 mAh. So, and our phone usually charges 4000 mAh. So we can compare it.
You can convert because there's a time unit missing there, but time unit you can pick of any time. But you will agree that the amount of energy which we have consumed is significantly lower than what your electronic devices consume. Particularly for imaging. And the quickest way to destroy your phone as well, the easiest way to measure was just take a non-stop video and see how long video you can record before your battery dies. So you can go to a station, and if anybody starts troubling you while you're taking pictures of random people, you can just say, I'm doing an experiment. German guy told me, what can I do? No? Okay. Now, the other thing which is happening with digital cameras is we're increasing the amount of things which we're doing with digital camera. We're increasing the number of pixels. And this gentleman now wants to apply software and AI behind it. Something more is taking power. And we are increasing the amount of energy needed. The more AI apply, the more energy we need. Good. Cost. Cameras, sensors cost $3 to $4 US. I don't think we can put a price on human eye. It would be wrong to put a price on cameras. It's not noise. We don't know what's the noise in human eye, to be very frank. I wrote a couple of papers predicting what might be the noise. In digital camera, we have got fairly high noise. The way we correct for the noise before you see the image. Even in the ones which don't have software and AI, we're still doing at least correlated double sampling, and we'll see what double sampling is later. Now, I have a theory that we have noise in human eye as well. Our brain corrects for it, and the best way to know this is the wrong question to ask, but for scientific purposes, we can ask the wrong questions. Have you guys ever got drunk? It's a random survey. We're going to say yes even if we get drunk. Huh? Now, most people start seeing hazy when they are drunk. They don't see clearly. So what actually happens, the scene starts becoming more noisy. Your ability to discriminate low contrast starts reducing. Let's take a nicer example than making your own. Okay, I did not say go home tonight and get drunk for this experiment purposes. Just 5 bottles of wine, still not drunk. We need few more for the experiment to take place. How many of you have had laser surgery done to your eyes? Anyone? Nobody? So post laser surgery, we often advise, or post any eye surgery, we advise people not to drive because your depth perception has not improved quite well. So I think there's noise in human eye. As we grow old, our resolution also starts degrading. Cataract is a very good example. People suffering from Alzheimer's and Parkinson's also suffer from this. So there's something noise in human eye as well. After waking up, yes, I think the eyes have opened, the brain hasn't opened. That's happening with most time for me. You're right. Speed. That's where digital camera is good. Human eye is kind of limited to 30 frames per second. You can't do very high speed video. As soon as the fan starts rotating, oh, there's no fan here, it's not rotating. But you know, when fan starts rotating, we see it as a continuous motion. We will not see it. So our speed is good. We can't increase our speed. Cameras, we can go high speed. We can do 1 million frames per second. Color. Okay, so human eyes color perception is terribly unique. This despite the fact each one of us have a different number of cones. So now I said that cones are the color centers of human eyes. We have red, blue and green cones. I might have more red cones and he might have more green cones. The number is different in each individual. But somehow, both of us will say that color is kind of red. So somehow I've learned with our different spatial sampling and our processing. So you keep same classification to different colors. Now, should we do a color experiment? Now, so we do a color experiment with your phones, and I'm trying to see. The thing is, even I'm getting a very black color, which is the worst color to do any experiment with cameras. You know, it's black. There's nothing more you can do. And all of you guys are very boring color as well. So should we go shopping spree this today? Buy t-shirts of bright color. All those in favor of shopping? Even my girls are engineers, and they don't like doing shopping. Okay, generally our color performance is improving, but it's not as good. And I promise we will try to do color experiments soonish with your mobile phone cameras to see how good or bad it is. The other thing is, for you and I, we have got what is called as global shutter. Essentially, we take the whole scene as one image. So it's not that I start reading from that screen, that pixel, this pixel, and so on. Whereas most cameras have got rolling shutter. They record one pixel, then they record another pixel, then they record. By the time we have moved down, the scene might have changed for high-speed moving scenes. I will show you examples of this in slides. There are a few things which cameras are good. One of them is region of interest. So for us, if we want to see that a particular thing, we need to move our head. So mechanical region of interest. Cameras can take the whole picture and then you can zoom in one region. So our highest sensitivity is right in front. If you want to see more clearly, we move. So most of you are looking at me. If I ask you to tell me what's written in that slide, all of you will move your head. Whereas if it was a camera image, that and that would have been together. Okay? Optical assembly, I talked about. The human eye has a very simple optical assembly. So simple lens and that's it. Integration. Now this is where human eye is way beyond our digital camera system. It works smoothly with the brain. It has grown with the brain. So little babies, they cannot see color. They can only see till this distance, newborn child. This is why when you hold a newborn child, you try to bring them close to your face. That's what they can see. Beyond that, everything is useless for them. But the eyes and the sensor, the processor, they both go together. So they both learn to complement one another. Like if one is weak, the other one compensates for it. Our cameras are designed without thinking where the data is being processed. Which CPU is doing to deal with it, which GPU, which algorithm. None of this is thought while designing the camera. So they're disjoint system. And this is why the system integration is way better in case of analog. Manufacturing time, that of course is a joke. Human eye takes at least 9 months to manufacture, almost along exactly. Cameras 3-4 years. But we have evolved over billions of years. We have reached to this stage over a billion years. Okay. So I said in the morning that I'll talk to you about our desire. So this is the sensor as itself. Now let's see how we have reached where we have reached today. Before we start looking at physics. So these are some of the earliest images which we started taking. So oldest came in Europe. We were drawing things 30,000 years ago. People started drawing things. We wanted to record what we see. And that's where cameras are useful. We want to record whatever we have seen. That's the picture from the oldest surviving photo frame. That's one of the X-ray images of Wilhelm Röntgen. I visited his X-ray lab in Würzburg. Very fascinating place. Remember, is this the picture of, there's a ring, right? There's a ring in the middle finger. Do we see a ring here? So whose hand do you think it is? The ring should give something. Yes. It's his wife's hand. Okay, so moral of the story, X-ray can be harmful. Moral of the story is if you discover something which can kill you, try it on your partner first. married here? Those who are married, they all say yes. No doubt. Those who are unmarried, they're like, what's wrong with these guys? Okay, so let's look at a bit of camera history. Now, generally in engineering, we never talk about our history. We don't talk about famous engineers, we also don't talk about our history. When you guys teach, do you teach the history of circuits? No. You go straight into, here is a bipolar junction transistor and MOSFET, and same when we did our courses. But there's a reason we should know history, and I'll tell you why a bit later. It's also a bit fun to know a little bit where we are, why we are. So that is the first digital camera which was showcased. This is not the camera. The whole damn thing is a camera. Okay? It comes with a tape to record images. Some of you who are older might remember those tapes when which songs were recorded. Okay? So this was a specification. It was only 4 kilogram heavy. It could do black and white images, and it had a special screen which you had to buy to display the images. It was only 1975, not that old. We're 2025, right? So only about 50 years ago. It's exactly 50 years ago. We just celebrated this year. It had 0.01 megapixels, and you had to stand still for 23 seconds to take a picture. Brilliant, isn't it? Try asking me to smile for 23 seconds. This was not certainly, it was not very successful in the market, but it was a good attempt anyway. So this was the first consumer camera which actually became successful. This came in 1988, 11 years or 19 years. Now this was Canon Sharpshot. Only costed $1,000 with everything, because if you wanted the battery, the floppy disk and the cable, everything added together, it will be $1,000. Still very costly, right? We couldn't buy at that time. Are there anyone who was born after 88 in this room? Anyone born after 1988? One person. Oh, a lot of people. So this is before your time. Okay, we don't know anything about before our times. So this is what people could start buying. Now we're going to 1990s. A 0.09 megapixel camera costs about $995. And then very soon we are seeing things increasing resolution. So by 1991 we have 1.3 megapixel camera. Now this is interesting. So look at 1995 Apple Quick Take. It could take 8 pictures because it had a 1 megabyte flash memory drive. For 8 pictures, you need to pay $750 US. You can imagine why these cameras are the preserves of only rich people. Now, we're coming to the days of mobile phones. Now, cameras are being made in kind of similar technology to which our processor and memory is made. They're still silicon based. Till this time, they are made out of an older technology called charge coupled devices. We're going to CMOS devices very soon. Now, this was the first mobile phone camera, which was Samsung SCHV 200. A 0.35 megapixel camera, and you could take and record 20 photos in it. That's about it. I hope you can hear, still hear me? Can you hear me? Yes. So Sharp JSS04, this was a 0.11 megapixel camera. It was included in better? So history is one of my interests. And by now you have realized, with electronics will be, when will these guys actually start teaching? So, when this camera was launched, I was looking into the history of my own field. I found a BBC News article which talks about this is exactly the news article from 18 September 2001. I'm sure by 2001 many of you were born. Right? Maybe I should start talking in that house. Darth Vader sound. Better? Not better? She doesn't like me, sir, it just likes you. Okay. Now the other thing which you see in newspaper articles. I'm hearing my own sounds a second. Listen. Sir, do one thing. That is needed only for his screen, right? Bring it closer to his computer so that we can keep very low volume there. Does that make sense? No, what I meant to say was, if it's closer to the computer will pick up the sound and that's all we need it for. Keep it here, we'll have echo. No, it is better. That's good, sir. Okay. So most news items also have this consumer thing, right? Where people write their own feedback about how people do write and blog entry. So on those days, BBC used to have this comment section where people can comment. And you see, the news item says things like, the Japanese are crazy about taking miniature pictures of themselves. BBC not being racist, huh? Some of you got the joke. And this is the first camera phone where you can take a picture. And this was a very interesting one. I looked at people commenting on it. And here are some of the good comments I picked up. Infinite use for the teenager. Not entirely sure what the rest of us would do with one go. So in 2001, people are still not sure. Why do you like to have a camera on your phone and send it to somebody? Okay. But that's a very good example of how the market is not always right. Market did not know. We created this market. The whole market of taking pictures and sending to your friends has been created by the availability of cameras. To an extent that 2013, the word of the year was selfie. It kind of saved gave me a new professorship because by that time the back phone had become fairly good. Now we have got a new place to put your cameras, the front. So we needed more cameras than one per mobile phone. Right? We're still having, only now we are having 2 screens per mobile phone, right? The flip phone. But 2 cameras are box standard for last 20 years. So the front camera in iPhone 4 was, it started getting, you started doing FaceTime, but I think the first Sony's flip phone also had a 0.3 megapixel camera. Now, none of this is factual in the sense that you can't use this for any patent fight between Sony and Apple, who did the first phone. So we'll take it as an academic record rather than using my word against one another. The question is, where did it all start? When did we all start taking pictures of ourselves? I'll show you some examples. painters started painting themselves in their pictures. Very famous. So this is Velázquez, who has painted himself here. So in old days, rich people used to hire painters to paint themselves, right? Or kings and queens. The only way for you to famous is if you can somehow paint the picture itself. So that's Botticelli, wherein he has painted himself here in the corner. The most nice looking person. Now, do you know any of these? Some of you might recognize the middleman. What was the first one? You know the first one? Fine. I was going to put another portrait, but I'm trying to see how quickly I can transfer this thing. Let's see if you can identify those other. Oh, people have already started their Gemini search. All right, tell us, what does your phone do? So who are these three people? No? Not yet good enough? Second one is easy. Vincent van Gogh. Right? That is easy because of the lines which he used to draw. Okay, I don't have, do I have puzzle available? Oh no, I have removed. Okay. Rembrandt. Okay. Let's stick to it. Now, even with earlier camera types, we get used to the earlier mechanical cameras were daguerreotypes, which basically has silver halide films which are come. People have already started taking pictures of themselves. Cornelius, John Gabriel Peinart, and you can see people who are somehow trying to take their own images. To an extent, Kodak actually sold a camera called Brownie Box in early around 1900, which can help you take your own pictures. You can use either a big mirror, or you can use pictures from your own self. And of course, you can use mirrors of different type. You know who that guy is? The other person? Stanley Kubrick. That's me when I was still looking young. From my own camera in 2002. And people do crazy things to take selfies. That's not new either. That's 1966. A guy tied a camera to his feet, went up in balloons to take that picture. So any parent generation who tell the modern day kids, they have gone bonkers. People have gone bonkers for a long period of time. So you provided an option to take pictures, people will take pictures. Again, it's not a terribly new thing. With that as a background, so cameras are not new things either. One of my first grant application when I applied in Glasgow was reviewed by an internal physics professor, and he had this famous line. It was 2009, cameras are not that popular. What's new in cameras? Einstein discovered photoelectric effect. We know light can be converted to energy. What's the big deal? Now the big deal physics part was done many, many years ago. And that you should know. All right. This is now coming through my ears. There's only so much finite capacity a human brain has to hear of their own sound. Unless, of course, you're a politician, then you can hear yourself the whole day. So we know that thing fairly well, don't we? Light falling on a metal or semiconductor will lead to, light has got energy of its own, each photon has certain energy. It falls on any surface, it passes on the energy. As long as the energy of the photon is more than the work function of the metal, it will give the energy to the highest electron in the outermost orbit. So the electron in the outermost orbit give the energy and the electron will be free to conduct or free to move. And a moving electron is current. If you can move an electron, you have got a current. But if you can move a large number of electrons, then you have got a decent amount of current. So that we know. The other thing which you should know by now, and I'm going fairly basic now, is from the semiconductor theory we have this thing called band gap. Most of our students hate derivations of band gap in early days, right? Anyone love those? Anyone remembers those? Smile says, nah, please don't talk about it. There are better things to do in life. So, you want to say something?
Rembrandt, the first one.
The first guy was Rembrandt. I told you that. Who was the last guy? Hermes. Or am I getting a loop? Have I been time shifted 15 minutes before? So they should have come across that structures have, well, in a very basic background, we have valence band, we have lots of electrons. There's a conduction band. If we have an electron in conduction band, it will move. If you can somehow move an electron from valence band to conduction band, that material will conduct. So when this energy gap between these two is high, they are called insulators because very difficult for electron to move. You need to give a high amount of energy for things to move. If you have got an overlap between conduction band and valence band, it's a metal. You give little energy, the electron is free, it's just waiting for some energy, and the moment it gets potential difference, it starts shattering. Something in between are the semiconductors, which have got a decent energy gap. The electrons is not free to move, but provided some interaction, electrons would like to move. So if I give a photon with a certain energy hits the one in the middle, it's a semiconductor. If the photon's energy is more than the band gap energy, it will lead to an electron going there. And in semiconductor, what else happens? There's a free electron. Every time an electron gets formed, a hole also gets formed. So we form an electron-hole pair. Okay? So, and that tells us the first thing about photoconduction, or capturing light. If I can have a semiconductor whose band gap is such that, now, each wavelength of light has got certain energy. So what wavelengths can we see? We're trying to take a picture of things which we can see to start with. So what wavelengths can human beings see? Visible light, what is its wavelength? $700. Is it single point 700? So white is not a color. It's a combination of colors. Right? So 700 watt. What unit? Nanometers? So somebody has done Google search. 380 to 790, did you say, or 780? 780. That's good. Look, it's perfectly fine to do Google search to find questions. We're not doing an examination. In my examination also, I make it perfectly fine. You're going to, if you're working as an engineer, you should have everything to search for. I don't want you to remember everything. I don't remember half of what I'm talking about. So somebody said 380 to 700 something nanometers. 740 nanometer, did you say 780 or 740? 780, 740.
390 to 750.
390 to 750. Brilliant. That's a brilliant answer because you're already being confused a little bit on where the boundary is. Okay? And you will know why we are being confused very soon. So anyway, so what's the energy of photon which is traveling with this wavelength? So now I will get, so it's 380, let's take for nicer calculation 400 to 800. We all love nicer calculations, right? What's the room temperature called? When you do calculations of room temperature, what do you take as room temperature in India? 27. Why do you take 27? Becomes 300 Kelvin, right? In Europe, when I came, everybody was doing calculation with 20 degrees Celsius. These are mad. Because that's the room temperature. You don't keep 27 degrees in a room, right? Because 293 is a difficult number to compute. But anyway, so let's take 400 to 800. Or you can take 350 to 700. Which means we have an energy, there's the lowest energy and the highest energy of a visible photon. Let's calculate that now. So if you want formulae, I will give you a formulae. Essentially, we can also do hc by lambda, where h is the Planck's constant, c is the wavelength of light. And yes, you are going to compute. If you don't have pen and paper, work with your nearest neighbor. You're a bachelor student, you don't have pen and paper. Where are you, bachelor student? Here or in somewhere else? You're here. You can make your life miserable as a revenge of whatever has happened to me. Right, let's do the numbers. And you can use a calculator of any choice. You can even use online web page. So I just want to know what the numbers are.
3.1 electron volt to 1.55 electron volt.
So I've got one number, please keep it in mind. So 3.5 electron.
3.1 electron volt at 800 nanometers and 1.55 electron volt, at 800. Yeah.
So red, which is red? What color is red?
7.
So we said it's 380 to 750 or something. So that is the spectral range. So each color falls in that range. So red is the higher color. Okay?
Has the lowest.
So red has low energy.
Yeah.
This is funny because we generally assume red color, people who wear red colors are people with loads of energy. We equate red color with blood. Right?
Yeah.
And I like red, so very soon you will see me. Today I was trying to be a bit formal. So the energy of red electron is roughly 1 point something electron volt.
1.7.
And the other one, so I've got one number. Let me see another numbers. And those who have done that, let's now try to find what's the band gap of silicon. That answer I get immediately. That was part of the questions. So what number did you give me? 1.1 to 1.21. Loudly. So one thing which Indian girls need to learn is to speak loudly. I know all your professors and your parents say be soft and gentle mannered. Stop listening to that. This is what hurts our Indian girls when it comes to campus interviews, because you're still soft and shy. Be bold and brave. Be ready to beat the hell out of somebody. Okay? So the number is 1.1 electron volt. 1.1 electron volt is that of silicon. Okay. So band gap of silicon is 1.1 electron volt. Which means if a photon comes with any energy more than 1.1 electron volt, an electron hole pair will be created. And that's actually fantastic news, at least for electronics engineers, because the only material we knew of was silicon. And we can look at band gap of germanium on that one. Let's find what's the band gap of germanium? 0.7. By 12, what's the band gap of gallium arsenide? 1.4 electron volt something. So that will not work that well. So by now you have done your energy calculations. What's your number? 1.65 electron volts and?
For red.
For red. What's the highest for blue?
For violet it is 3.1.
3.1 electron. Now you see why we call it infrared, things which are lower than red in energy or in frequency. Right? And we have ultraviolet. But one thing is true. Our silicon, if we make a sensor using silicon technology, it will capture red. And it will capture blue as well, and everything in between. Okay? But more is the energy my photon passes to the electrons. More is the power which I will be accepting on the other side. Okay? And that's actually what happens. So if you look at the spectral response of, this is a classic silicon detector, you can see at around 1000 nanometer it starts falling down. Okay? So below this, it has a decent response. It starts falling down, it becomes zero. So very deep infrared we cannot record using silicon. Okay, so that's why you can't make an infrared camera, but you can use near infrared camera using silicon, but far infrared cameras you can't make using silicon. So that's the other end, one end of the story. But you also see this has started to fall down on this side. Keep an eye on the time. It's already 4 o'clock. Oh, there's a watch behind me. It's actually my ear to tell to the students, stop talking. So we will take a break in a few minutes, okay? So that we can go out and stretch our legs. Let me just finish this slide and then we'll take a break. Something is happening on this side as well. So the photon here has high energy, but I don't get any current from my detector. Now something similar to you should have been taught in many bachelor classes. Has it been taught when it was photoconductivity? No? It was not taught. The classic answer for all final year students, has this been taught in second year? No. Right? Fourier transform? Don't remember exactly Fourier transform, what was taught in the second year. So the reason why, so on one side, the photon doesn't have high enough energy to excite the electron hole pair. Now what happens as we are decreasing the wavelength of photon? Each photon is having high energy, right? But remember we told one photon will only lead to one electron hole pair being formed. Whatever amount of energy I have. So what happens as we go lower, remember the unit here is ampere per watt. Watt is the amount of light falling on my structure. So hypothetically, let's say for 1 watt I was getting 1000 photons in red. In blue I'm only getting 10 photons, so 100 photons. So yes, my photon has enough energy to excite, but my number of photons has fallen down for the same amount of power. Which means if I need an ultraviolet, it will be a good ultraviolet sensor, but I just need to give too high energy for it to work. So as a result, silicon works fairly decent in visible ranges. So that's the first point which we figured out, what kind of profile my silicon detector will have. It will go up after red, maximize in between, and then fall down. And it's also a good news for something else. So at one side we said there is blue or violet, one side we have red. What do we have in between? What colors are there in between? Indigo is close to violet, right? So in between red and blue, what do we have? Orange is close to red. Yes, good. Move on. Yellow is also closer to red. Green. So green falls in between. And it so happens our human eye is very susceptible to green. We see green very clearly. Nothing to do with religion. Don't proclaim that I'm proclaiming one religion or the other. We grew up in a forest where there was green all around us. So our eyes learned to look at green. We didn't have red color leaves, there are some, not most. So they are quite nice to read. This is why silicon becomes a very nice material. High sensitivity in green can capture red and blue. We can make a camera out of it. Let's take 5 to 10 minutes break now, okay? And then we'll start again. Happy? Good evening.
I just have a tea outside. 5 minutes break to go outside. Have a tea.
Right. So we ended up morning session with looking at silicon as a material detector. Now we are going to make the picture out of it. Okay. Now, kinda going to assume a number of you know. Don't worry, we'll see. I'm not going to assume anything. Assuming anything is dangerous. So I give pictures of many painters, just one more painting, just for fun. I knew you could not identify painters from Europe, but let's see if you can identify this gentleman. Somebody? Looks fairly. Stop Gemini for that. Stop Google search. That's not allowed. Google search was allowed for the Europeans. If you can't identify your own person, then he looks Indian, right? The topi and the thingy and the stick, everything is Indian. So who is he?
Raja Ravi Verma.
He's not Raja Ravi Verma. Then I was going to tell you, do you recognize these two paintings? Who told you Saraswati looks like that? That's Saraswati and Lakshmi, right?
Yes.
We all assume Saraswati to be like that, with a veena in her hand and a peacock on the side. We almost always assume Lakshmi to be like that as well. Not only that, we have these things in our mind of Kali and Lord Rama, with Hanuman sitting in front of them. Who told us they look like that? Raja Ravi Verma. We basically make copies of his painting and imagine gods to be like that. Remember, we didn't paint gods in past. By Indian tradition, we made sculptures. Now, sculptured gods don't look like this, do they? Next to Saraswati, you don't have a peacock sculpture like that. So it was Raja Ravi Verma's contribution which made us believe, and that's why, that's the sign of a great painter. You don't know the painting, but you all know the drawings. At least those of Hindu tradition would know, and even those not Hindu would have seen this sometime or the other. Good, back to technology. So, imaging or camera making has been there for a long period of time, but it became very different in last century. And only about 100 years we went through 3 different technological reforms, 3 different ways of taking pictures. And all 3 were heavily successful. 2 of them are not even there in market anymore. Okay? So that was the first, the reel based. Right? So they were kind of a chemical process. They're actually quite good cameras when it comes to dynamic range, bright and low light, and single shot. So global shutter. So when you switch on the mechanical shutter, it took the entire picture at one go. So it was not very bad camera, but the limitation was the number of cameras images you could take. Now in the 50s, we were trying to send the first space-going telescope up in the sky, and reel doesn't do very well with gamma radiations in the space. And that's when we started looking for a semiconductor-based detector. So the first to become market successful was this guy, charge coupled devices. The way it operates is it kind of looks like banks of capacitors, so banks of PN junction one after another, each charged to a different voltage rate. And then light falls on it, electron hole pair gets generated, you store the electrons, and then after some time you move the electrons from one well to another. and very much your faces are saying, why is he going that fast? Everything else was so moving fast because they ran for about 40 years. And they are also a dying technology now. They are not the technology used in your handhelds. The one which we use quite frequently in your handheld are pure CMOS based technology, the same technology in which we make all our processors and memory. Somebody is fighting next to us. Is the noise fighting, sir, or is it just entertainment? Is it tea stall next to electronics department? That's an insult to electronics department. Do they give free tea to us? Should be bad. Well, see, I don't drink tea, so I can afford to ban them. Wait till I become the director of this institute. The first thing to be. So, if we use spending most of today, tomorrow, and possibly half of day after tomorrow, spending on CMOS-based imaging technology. Now, the reason why we use CMOS is CMOS has generally got MOSFETs or transistors of some sort. But there's always a diode. There's always a P junction, and a P junction of any type will act as a diode. So it has diode, but it has very poor optical responses in past. But it has some promises, and the promises were, as the transistor becomes smaller, the diode also becomes smaller. So we can have more and more pixels in the same camera, which is very nice. As transistors become smaller, the power on which they operate, the voltage range goes down, which means we can have lower power operation. The cost also goes down because memory and processes, their cost is going down. So my camera cost will also go down. But the biggest promise was this. We could make cameras in the same technology on which we make a processor. We can make processor and camera on the same chip, so that we can do image processing as we take the image. We can do a focal plane array or a human eye. That was the promise. We ended up completely not living up to that promise because our market said, forget about processing, just give me more megapixels. So we ended up taking the entire chip area just for pixels. Right, so some basic stuff about transistors. Can I just forget talking about transistors, diodes? Is everyone clear on their operation? So I'm getting the mantra yes, which is a pendulum motion. No or no? Because you see, this is no in North India. So every time I come to India, I have to recalibrate my operations thinking. So the way I could differentiate between yes and no in South is if it's a undamped pendulum motion, it's yes. If it's a damped pendulum motion, dies immediately, then it's a no. Right? This is interesting because we do quite a lot of pendulum motions in our life. This is pendulum motion, right? It's a non-linear pendulum motion. Our heart is a non-linear oscillator. Actually, both of them are examples of van der Waals oscillators. So I'm going to run through, assuming you guys know about transistors and diode, and that's the only thing I'm going to imagine. Don't worry, no more harder circuit complex than that. That's the CMOS inverter. You have an NMOS in the bottom, PMOS on top, and that's how transistors are made in 2D process. So in order to make a transistor, you will have two N-type doping, a P-type substrate, put a thin silicon oxide, put a metal contact, or metal or polysilicon contact, and you have an NMOS type transistor. To make a PMOS type transistor, you do the same thing but exactly opposite in N. Okay. Not of interest to us, but I just want to show what is of interest to us is this. Is a P-type substrate. In order to make the transistor, I put N-type dopant here. I'm already forming a P junction. This is going to be sensitive to light. Light falls on it. Electron-hole pair will be generated. If I bias it properly, electrons will move one side, holes will move one side. I will get a current. So I will get a current with light falling on this and on the diode. Don't get me wrong, we can also make phototransistor, we can make photoconductors. But we will be looking simply at diodes. Now I've got some more diodes here. I have got here a diode, and I've got a deeper diode here. So already I'm getting three different types of diodes. An N-well P sub, N plus P sub, and a P plus N-well. And if I have a triple layer technology, which I think the UMS process is, or which we are going to work, you'll have P-well here as well. And sometimes we have a deeper N-well. So any CMOS process gives you options of many different type of diodes. We're not looking at FinFET process, we're only looking at bulk process right now. Now, we designers really don't like choices. We are like men. Our trouser collection consists of black trouser, white trouser, and blue trouser. Right, guys? You know how hopeless we are. So there is a problem. We already have three different types of diodes. We need to choose one of these. Good. The other thing which we know how diode characteristics looks like. In the forward bias, it goes exponential up, and the reverse bias is kind of fixed with bias voltage. Right? Now, the amount of light falling on the diode is going to, if we have a standard light like this, what we have in this room, it doesn't have very high number of photons. It has high, but not high enough to lead to a very large current. So it's a small number of photons which are falling into. Not very small, not even one photon each. So if we are in the forward bias region, where the current is already very high, the current goes up exponentially. So operating the diode in forward bias means I need a big change in current to notice the current. But it's exponentially rising anyway. It's much better to be in the reverse bias region where the native current, the reverse bias current is small. So any small change in current, I'll be able to see. Essentially what happens is if that's my no light curve, light falls on it, that curve starts falling down. So I've got more current flowing in. Okay? So that can now act as a silicon detector. A PN junction will be. So the simplest camera you can think of is why don't we make an array of these diodes? Okay. The only thing which I need is I should be able to read from each diode separately because each pixel is a point. So I need some sort of a switch. What's the simplest switch I have? A transistor is a switch. Right? If you apply a voltage lower than threshold voltage, it does not conduct current. Okay? So a simple NPN transistor or a PNP transistor can act as a switch. The simplest camera I can design will be something like this. I've got these diodes to capture light, and I've got a switch next to each diode. The switch either stops this light current flowing here or stays here or allows the current to flow. And then I can have, because I've got many rows, right? I'm trying to take picture of two dimensions. So I will have rows and I will have columns. So let's try to do kind of a row decoding. So I select first row first. Then the current output of each of these diodes start falling through these column lines. So rather than 2D array, now we convert it into a 1D array. And then in the column line, I can have another multiplexer to somehow say, okay, first take this current. If I have a current, how can I convert it to a voltage? There are many ways. I can pass it to a resistor, I can pass it to a capacitor, get a voltage difference. So in one of these ways, I convert this into this is a voltage to current converter, I can convert current to voltage converter, I will get a voltage output. So first I select that row, then I select this row, I switch both of these two off. Now I have the current of these pixels and I have got it out. The simplest camera I want to make would be an array of diodes, each with a switch. Done. Let's go home. So anytime the professor says this is a simple way, you know what's coming next, why it doesn't work. Actually, it kind of works. It's not a bad camera as long as you want less number of pixels. Let's do some calculations to see when does it start causing problems. Some of the early cameras were arrays of diodes, nothing else. So I'm not going to force you to do this calculation, but hopefully I've done the calculation and you can visualize. I don't do much calculations, you will not see many numbers, but you can see that. So we agreed that energy of a photon is hc by lambda. So I made you do that in the morning. At this point you might say, if you're going to do this anyway, why did you make us do it? I can answer to that because I can, I'm a professor. So I took 600 nanometers somewhere in between. That comes out to be around 2 electron volt. Silicon will give current impact. Now, so that is the energy of one photon. Now I need to know how many photons are falling on my detectors, because the number of photons will give me number of electron hole pair. Once I know my number of electrons, I can calculate my current. So if I now go by this relationship, which is how many number of incident photons are there. So energy of each photon is h nu. The total power of incident light is power. Divided these two, that gives me number of photons per second. And I know number of photons per second is going to be equal to number of electrons per second. So going by that, I do get a certain number of electrons per second, in this case 38,000 electrons per second for a typical power. Okay? And that when I multiply with the amount of electron charge gives me current. So each electron has 1.6 into 10 to the power minus 19 coulombs. That's the number of photons per second. So charge per unit time is current. So I get a current of about 6 femtoampere. That is a fairly small amount of current. It's not negligible, and that's the level of current which we are going to play with. We're never going to deal with more than nanoamperes of current. So all of you should be familiar with nano, pico, femto, atto. Now there lies the issue. So we're only going to get the 6 femtoampere. That will depend. I will have to take for a typical light level. My light level is low, I will get low number of current. If it is high, I will get high amount of current. Now let's ask, this is called a passive pixel sensor. There is no active circuitry here. There's just a diode and a switch. So let's now try to ask our question. Let's see bright light, because in a scene you will have different things, right? There will be some bright light. There's bright light here and there's low light. Let's just take 2 pixels. So bright light means high current, low current. So high current falling on this. Now this current moves through this path till this point. The path will have some resistance. I cannot make resistance less paths. It will also have certain capacitance, because I now have a long wire running on top of a ground plane. That is a capacitor for me. It's a parasitic capacitor. Okay? So any wire is a capacitor. Now, of course, this is a wrong statement to make in first year bachelor lecturers. To make capacitors, you need 2 parallel plates. What we often forget is ground can be a plate as well. So I have a resistance of the wire, I have a capacitance of the wire. It immediately forms an RC circuit. An RC circuit takes time to charge. Again, second year electrical engineering, you apply a voltage on RC circuit, it takes exponential charging time. And the charging time of an RC circuit depends on the amount of current you are giving it to charge. Right? Same with the discharging cycle. It has to discharge through a circuit. So a high current will charge this RC network very quickly. The low current will take a large amount of time to charge it. If this wire is long, if I have megapixels, to make a megapixel I need 1000 rows by 1000 columns. That becomes a megapixel. So if I have 1000 rows, which means this wire is 1000 times the size of each pixel. Now I've got a high capacitance to charge. So the small current will take a long amount to charge, which in turn means I need to wait till my line is charged before I can move to the next line. So the overall speed of the camera becomes very slow. Now remember when I talked about the first digital camera, it said it took 23 seconds to take a picture. Why was it taking 23 seconds? It was a passive, kind of passive pixel sensor. Okay? So all these numbers which we are going to talk about should have a scientific foundation. So passive pixel sensor will kind of work, but will have different charging time in each one of them. There are a few more problems with it which we will see later on. Let's jump on to the sensor which actually makes sense. We'll start with a 3 transistor pixel circuitry and then go to a 4 transistor pixel circuitry, which is in front. So our simple pixel, most pixels used in camera phones or mobile phones or phone cameras general are based on this design. It starts with a photodiode which carries current. But we don't now want to read the current at all. Problem with current reading was this: the current has to charge all the column line. We don't want the current to charge column line. So what we would like to do is we would like to convert that current into voltage in the pixel itself. If I have a voltage, I could drive a higher amount of current through the voltage to read. So what we do is we do this. So we now have a reset transistor on top of it. So till now it looks very much like our passive pixel circuitry. But now I connect that node to a high voltage. That could be my VD. Right now it is a VRST. That could be my power supply. Okay. If anyone understands, stop me then and there. If you don't understand, there's not going to be a crime. When actually designing this in cadence, at that time you forget what about you. That is going to be a crime. And then what we do is what we ask is, this diode also has a parasitic capacitance. Agreed? Reverse bias junction has got a capacitance of its own. So let the photo current flowing through, let the photo charge being produced flow through this capacitance. It can't flow through the capacitance because capacitance blocks DC current. So what will it do? It will store the charge. All the negative charges will get stored there. Okay. And because it's charge stored on the plate of a capacitor, the moment you allow it to move, it will form a current. Or it will become a voltage. So now, and after that, I have got a very simple source follower circuit, followed by another switch to select this particular pixel. Let's see this operation in a bit more detail and then it will become slightly more clear to you guys. So we start the operation by pushing this signal high. So I apply high voltage, this transistor becomes on. That voltage kinda comes on this node. I said the word kinda because the node is a VT drop, so it's not exactly the reset voltage, but it's a high voltage. So what I get is at the reset time, this node N1 becomes high. This is a select switch. It just selects to come on this one. This is a source follower circuit. I put the input at the gate of the transistor. The output is taken from source. What is the gain of a source follower circuit? You guys say you know about transistors. Give me a number. The worst it could be, you'll be wrong.
Can you come again?
What's the gain of a source follower circuit?
Ideally, it should be 1.
1, yes. Nobody asks you any more complex gain. The only time a question like this comes is when the gain is 1, 0 or infinity. The only 3 numbers in our electrical engineering, right? Electronics. You don't need it. All of the numbers you have to calculate. So my trick is, and that's why I think I used to get jobs, was throw one of least one of them have to be correct. And if you don't believe this, my job interview, I got one of the higher paid jobs in this campus. They asked me to draw the layout of a NAND gate. And I actually drew it on a gate. I drew it with confidence. To the level the guys got confused and got me a job. Much later, I visited Alliance Semiconductor, and the guy who interviewed me met me there and says, "Oh, you confused me with the NAND gate layout." So give one of these three answers. What's the worst could happen? And I knew immediately after drawing it that as soon as the second question started, I knew I had done a mistake. But I couldn't go back and say, by the way, could you stop? Let's go back to the previous question. Couldn't do that. So that kind of has a gain one. So whatever voltage I see will appear here. Right? Input at gate, and this is just a switch. So whatever I see will appear here as well. Of course, I'm biasing it with a current which you don't see right now. The current bias can be bottom of the column. So let's start again. So I apply a high voltage here. This voltage becomes high. Then I switch this thing off. I remove this circuit completely from operation. Light is falling on the diode. What does light do? It produces electron hole pairs. Here I've got a high voltage. Let's take I have 3.3 volt. 3.3 volt is going to attract. I've got electrons and holes which will get attracted to 3.3 volt. Holes or electrons? Electrons are negative. They get attracted to the positive one. Right? So electrons go towards 3.3 volt. And what do an electron do when it goes to 3.3 volt?
It creates a current in opposite.
It reduces. 3.3 volt is a high positive charge. The negative charge goes there, it reduces that amount. Right? So my voltage starts falling down. More electrons comes. I'm assuming it's the same level of current which is falling. My voltage starts falling down. Essentially, I get a voltage falling down based on the amount of light which is falling. Slow light will slowly degrade it. High light will make it go low very soon. All the holes will be coming to ground. Okay. Now, there is a level this voltage cannot go below. And if my chip has the lowest is 0, it's cannot going to go below 0. There's no way that can go below 0. We'll see when it goes. But there's a level at which it saturates. Any higher light than this, it does not go 0 then. And this is what happened in some of the images which we took in the morning. Remember you took a picture of the bright light? We just got a white shape. So not only was this thing saturating, neighboring to this was also giving enough light to go immediately to the lowest voltage possible. Okay? So that's the saturation. So what we allow them to do is we allow this for a finite integration time. We allow this this voltage to fall till a certain point of time we call as integration time. And at that point we switch this voltage on, this switch on. Now this is connected to my output line. That's the thing which I read. I read the output here. And that is now going to be this voltage minus that current which has been flowing in it. Actually no. Why don't we do this analysis? So, everyone has a pen and paper? Let's do this anyway. I don't have a blackboard to write. Tomorrow we'll get a whiteboard somewhere. So think of it this way. Replace this diode with a current source, which is my light-induced current source. In parallel, there is a capacitor. Okay? Now let's write what is going to be the equation of this voltage. So I'll run through and backside. Then I have to remove this, okay? Actually, can we remove it for a minute? Let's see what happens. Is it a manual or is it a... Oh, that's much better. Keep on doing it. Let it go. Let it go. That's fine. punchline of one of the teachers here, Professor S.M. Ali Khan. He used to say the difference between a cleaner and a professor is cleaner cleans horizontally, the professor cleans vertically. Okay, let me something to write and I will be fine. Delete this as well. Who teaches this course? Oh, that's fine. He has done his quota of being angry on me. So we are now looking at this point. And this is actually brilliant. You can have a projector and do see lazy. There is something nasty. Keyboard was disconnected. Okay. So we're looking at this point, okay? And I said I can think of this diode as a current source. Let's call it I photo. In parallel with the capacitor, let's call it CPD. Okay? The current source looks as the photodiode, and on top of that, I have got a switch. This is becoming now my node N1. This is the same as this. So I make this N1 go to a very high voltage. Let's call it this VRST, and I just want to know what is the voltage of this. So now I know my voltage is falling down. That I know qualitatively. The voltage is falling down because this I photo is being integrated on this capacitor. So what will be that here? Will it fall down? High school maths, what's the current in a capacitor? So it's dependent on time. Right? There is no resistance in the circuit. Right? So dV is just going to be change in voltage. I could also call it delta V. Delta V is going to be IC times delta T by C. And delta V is whatever is the difference from T. So that will be IC divided by CPD. IC now becomes I photo times T. That's the last equation I am working on. So I thought I was not a bit clear. Next one you guys are working on. So that tells me what's going to be my output current voltage here. My voltage, and that has got a kind of gain of 1. We will see what's actual effect this is going to do. My voltage is V reset minus I photo times T divided by CP. If my T becomes fixed, if I say after this fixed time I'm going to record my voltage, CPD is not changing. Diode has got fixed capacitance. And reverse bias diode capacitance does not change any voltage. It does, but not too much. You can see my output voltage is going to be linearly dependent on my photocurrent. Isn't it? That is kind of fixed. So this minus photocurrent times something. I can call this as A plus B times my photo. Yes? It's just a linear relationship between input voltage and output. In the same breath, why don't we see the eraser? There's a reason I'm making you do this maths. I said in the morning I don't like complex maths, right? But we are going to see why the image quality degrades. We've already seen what happens when highlight falls. It saturates. If this voltage is very high, you just cover this whole thing. If this voltage is very low, it won't have changed by a high amount of time for me to measure. It have changed, but it will be very low amount of change. That only tells me what's the lowest current, what's the highest current I can measure. Good. Now, we're also reading this thing out. Okay? We are reading this thing through this source follower and the switch. The source follower needs to be biased somehow. The bane of existence of all second year bachelor student is what the hell is biasing. It took me another 2 years of research to understand it fully. Why do we bias anything? One of the reasons, can I take this quick break? So those who are teaching, you guys are teaching there, right? What do you teach first, BJT or MOSFET? In Warangal, what do they teach first, BJT or MOSFET? Still they are teaching BJT first. What did I say? Yeah. The quickest way to annoy a bachelor student is to teach him bipolar BJT's biasing circuit and quiescent point. No one understands that easily. Agreed? None of the textbooks are very nice descriptors. They just assume you know things. I mean, whenever you do the emitter bias, you say, assume there is 1 volt at the emitter applied and there is 0.2 volt drawing across collector and emitter. No one ever understands why. At least I never understood why it is done. Nobody touched it. So what I do is I do exactly the opposite. I don't teach BJT at all. And there's a big advice I'll give to all of the people teaching electronics engineering. Stop freaking teaching 18th century technology. BJTs are useful, but their market share is very small. They're used in high-speed circuits. So use BJT after you have done MOSFETs. So start with MOSFETs. Let life be easy for your students. They understand MOSFETs easily because they're fairly simple circuit. Right? It's on or off kind of thing. And then go to BJT. And this is what trick I learned while I was teaching in Oxford. My predecessors, they had done this many, many years ago. They always started with MOSFET in first year of engineering. Even before we do diodes, we start with MOSFET. They're much easier to understand. So with that logic, I need to bias it. So let's apply current source at this point. Let's call this I bias. So this is the current which will flow through here. Okay? This is the voltage I said will be appearing at this point. That is just a switch. So I'm kind of going, it's going to add just a resistive value. So I'm going to neglect its contribution for time being. The only thing which I have been left is this M2. So I know this voltage. I now need to know what's going to be my this voltage. Okay? So it's a source follower circuit. Let's see how many of you remember that calculation. So tell me what's this voltage going to be. So this I've already got. I know base current is flowing through this. I need to know that one here. If anyone needs a hint, I will be happy to provide. You need a hint. So what's the science saying in? Source follower transistor is operating in active region of operation. So we don't need to worry about linear or cutoff region. The current equation for a transistor in active region of operation is I drain to source is beta over 2. Let's not go the KW, the more complex one. Let's take out like simple. Beta over 2 divided multiplied by. Now we know why I say this is simple. That equation everybody understands. It's a simple equation. This is the threshold voltage of that transistor. Constant. Beta constant. The transistor is not changing, so its beta is not changing. Right? What's the gate voltage here? So what's the drain to source voltage? I'm feeding that drain to source voltage. Right? So I'm doing the reverse this time. Rather than measuring voltage, rather than measuring current, I'm measuring voltage. So I give my I beta. So that is already known. So that is my, that is my biasing voltage. By forcing a volt current, I am forcing the transistor to operate in saturation region. That's my biasing. Done. Let's start calling it beta 2 by 2 because beta 2 is the, beta 2 stands for beta of transistor M2. What's the gate voltage? Vn1. That's the gate voltage. What source voltage? That is kind of connected to my output. There's just a switch which is on right now. So if it is on, it's just a short circuit. That is my output. That becomes my V output minus VT2 squared. Now you get a derivation of V output. That you should be able to do. Do it. I'm making you do for a very simple reason. You will appreciate its beauty in a minute. So please bear it with me. And so if you put all of this, so first rearrange this so that you get an expression which says V out is equal to something. And then replace Vn1 with that thing here. You need to have it follow me. Oh, you didn't bring a paper. What were you thinking I'm going to do? I'm just going to talk to myself. Right. Leave for today, but tomorrow if you don't have a paper, you will be seeing the bad side of me. What's the popular Telugu song these days, which I can force them to sing? So nowadays it was Tuniga Tuniga. I never understood the song. Then that and Anagana Akasham Undi. I don't understand, but I know the lyrics because every time I went to eat in the hostel messes, that's the same song they played. So if you hear the song so many times, you know the lyrics by heart. Good. Well, you can see it's not very difficult. You can rearrange the equations. See, not only I'm making you work, I'm making the poor cameraman work as well. Or else he could have just pointed at one location and then gone home. But now he has to keep on waiting with me. All those who think they have got a paper and they have got this really small notebook, bring the big notebook because we're doing equations. Equations run longer than 1 pages. And I'll make you love equations for a change. I promise you that. We don't do equations just throwing out. Whatever you will do, you will like it. Something like this. You would have got V output is equal to Vn1 minus Vth, Vt2 minus
2ID by square root of 2ID by beta.
This is the time being. Minus IPHT by CPT. Okay? That's the equation all of you have got? Yes. So what do we do in electronics when we start having a longer equation? One of these two things we do. Either we start ignoring terms, we do that, right? We make to our students answer, here's a long equation, then this, you can ignore. Or we start clubbing them together. I'm not going to ignore anything here till now. I've already ignored quite a lot by using that simple equation of transistor. The whole complex equation should have had more terms in it. But I do know this is constant. If I'm feeding a constant I beta, I bias, and beta is constant, so this is kind of constant as well. So these two are going to form a constant. CPD is constant. Time t if I keep constant for all this thing. And that is also kind of going to apply the same VDD to everyone. So I can still write this as a plus b times I photo. And just like a political party person who joins one political party and as soon as he or she doesn't get a ticket, joins the next political party, I'm going to change my words as well. Just now I said these are constant. Now I'm going to say none of them are constants. So this guy is gone completely mad. At one point of time, I really wanted to stand in political elections because I thought that would be really fun. You can say whatever the hell you want, and then people will fall for it. So yes, these numbers are constant. Vt and beta are constant. But what is our aim in making pixels? To make them as many as possible. That's what my customer wanted. Which means I need to make each pixel as small as possible. The size of the array cannot become bigger because that is dependent on the lens. How much can the lens focus? So the size of the sensor is the same. I want more pixels in it. I want to make each pixel small. Agreed? In order to make each pixel small, and inside the pixel, what do I want to be the biggest? The one which is capturing light. Remember, it's a 2D structure, so diode, transistors all have to. Which is the only thing which is capturing light there? Diode. So I want my diode to be as big as possible. Okay? Actually, we have got a number which basically tells the ratio of the diode versus the total ratio of the pixel. This is called fill factor. What percentage of your pixel is actually optically sensitive? Because those transistors, the source follower switch, they are not capturing light. We have to shield them because each transistor is phototransistor. So basically provide a metal shield to stop them from capturing light. So I want my diode as big as possible and my pixels to be as small as possible. The only way to do that is to make my transistors as small as possible. Now, there is a rule of the game that no two transistors are exactly the same. The smaller you make them, more is their variability. And some of you who have done electronics courses might have done things like Monte Carlo simulation. To simulate the same circuit many times, to simulate the effect of mismatch and variability. We will do that later on. But for the time being, it's safe to assume that two transistors are not going to be alike. And when we say they are not going to be alike, it means that their beta and Vt is not going to be the same. Which means for the same amount of light falling on two different pixels, the output of each pixel is going to be different. That's not a nice thing. So IPH remains same. Because of these things, I'm going to get a different output. But this output is not going to change with time. It's because once my transistor's threshold is different, it's being done at the manufacturing time. It doesn't change with time. It does, but many years of operation. Okay? So I'm going to inherently get a noise in each one of the pixel response. So A is not going to be fixed, B is not going to be fixed. This noise is called a fixed pattern noise. It appears as if a fixed pattern has been imposed on my image. And I'll show you an example of fixed pattern noise just in a minute. Now that was the pixel level. Now remember, I also told you at the column I need to select one column at a time. Okay, before I continue, so what time do you guys want me to stop? Is somebody came up with 6?
Yeah, maybe it's already 5. Another 5-10 minutes.
Another 5-10 minutes. Those without family will say 12 o'clock midnight. Those with family, if they go later, their wives and children will have nice words to say. So on the column side, you have a similar kind of source follower selector as well. So the bottom line of pixel looks something like this. Now we'll bring it down a minute. So that becomes my pixel. This has got 3 transistors and a diode. At the bottom I have got a column source follower bias. The bias could be a current mirror or it could just be a transistor. The simplest bias is I apply a voltage on this transistor. As well as VTA. So whatever was the voltage, it was pushed further down. So that by applying a PMOS source, we can push it a bit up. And then I can have the output of the whole image. I'm not spending too much time in the column circuit because that's not how we design column circuits anymore. Now we just put an ADC in each column. Okay? But had we designed it like this in analog fashion, each one of these are also having a different VT and beta. So each transistor introduces a new kind of noise to it. As a result, this is what we get. So if this was my true image, what I actually capture is this. Now you know when I asked you about if you ever get drunk, what do you see? So if some of you do take up my offer and decide to consume a heavy amount, alcohol is not banned in this state, right? No, not yet. Some states have alcohol banning. If I say this, I can go to jail. And one thing I don't want to enjoy is in prisons. I've already been in RC Warangal for 4 years. I don't want more. So an image is captured like this, and you can see there are many ways we call this noise. One is you see there's a pattern on it. Right? There's a straight line things. That pattern remains the same. We have to correct for that noise. It's not temporal noise, it's not changing with time. That's why it's called a fixed pattern noise. And B, it reduces something specifically. It has reduced the contrast of this image. Here you can see the difference between these two, and here you can't see the difference between these two. It's an image from my lab, and that's why it's a hopeless image, because that's what I could get. A Mr. Shine bottle and a white paper to show how my camera is working. So now in the noise territory, an image produced by our camera pixel is noisy. And we need to get rid of this noise somehow. If you go into noise territory, then the question next would be, what are other kinds of noises do you know? So now we're dealing with non-temporal noise. But there's always going to be a temporal noise as well. Because we have charge falling on a capacitor, the current is moving, we're going to get noise. And we are worried because remember the amount of photocurrent we talked about? Femtoamperes. We have very little photocurrent and we would like to measure every small voltage difference. So what other kind of noise do you guys know of? it's 5 o'clock, I can still talk. Maybe your voice I can hear as well. But I don't do any other type of noise. So in the morning we were having that display, right? And the microphone started producing a lot of noise. I thought that was the microphone taking revenge on electrical engineering professor. The moment he said that electrical engineering got more project than electronics, the noise went. So, what kind of noise have you read about earlier? Thermal noise? Yes. Flicker noise? Short noise? Right? These three noises would have been covered. Trust me, all three of them are going to. So, I will take it for we're not going to do quantitative review on this noise, but we will do a bit on what these noise sources are and then try to correct further. So, let's go backwards. Short noise. So where does short noise comes from? So you might have heard of DC short noise. This is the noise which is there in the power supply. Because when we say power supply is giving X amount of current, it means X, Y amount of electrons. But electrons are not nice people, they don't all travel together, they are like our bachelor students. They all travel in multiple directions, they all come at different times. When we say it's the number of electrons moving through a junction at one point is the current. Right? They're all not, they're moving slightly differently. That gives birth to DC short noise. We have got a problem here. We have got photons falling on our pixel. Photons also do not travel together. So I said 10,000 photons are hitting, giving birth to 10,000 electrons. They're all moving with a slightly different and not fall exactly at the same time. That gives birth to photon short noise. And that's a physical limit. I cannot make a camera which will be better than photon short noise, because that's what light is doing. So I have photon short noise and DC short noise. We also have DC voltages power supply. Fortunately, they are small enough for us to live with, but they are there. The other thing which we have is, we're not very high frequency people. I think one of you teaches RF circuits or works on RF circuits. At RF radio frequencies, you ignore flicker noise completely. As if it doesn't exist. It's 1 over F noise, the frequency is high. We are not high frequency people. What is going to be my T? Remember in these equations we had a T, transit integration time. What is that going to be for me? How many pictures do I need to take in a second? What's the worst thing which I want to do? I want to take a video. There's a video camera behind us. How many pictures is it taking in a second? How many pictures do we need to take to make fool of human eye? That's a video. 20, 24, right? Let's go with 20, it's easy to calculate. So I need to take 20 pictures per second, which means in what time I should be able to take one picture? 1 by 20, which is 50 milliseconds. So we are actually operating each pixel as 20 Hz. 20 per second. We're not very high frequency people. Overall also, the ADCs operate at 110 kilosamples per second. Again, not very high frequency. So we're going to get flicker noise in the readout as well. But the biggest killer is not that. The biggest killer is Johnson noise, as everywhere else. We get noise not during the time of capture. Remember I told you right in the beginning we reset the circuit. Okay. So some homework assignment for those who still want to see me on a Sunday. Try to go back into your books and see what's the reset noise in a simple RC circuit. So you have a resistance and capacitance. Just see the noise. If not, we will derive it tomorrow. But that's the only noise which I see. And So today we saw how to make a pixel. We are done with pixel making, to be very fair. I can put you in the lab and start making the pixel. Because the design is not that very difficult when it comes. So we'll do a bit of more theory. But think of it this way. I've already told you, I need the smallest size transistor possible. So you can go in a technology, pick what is the smallest transistor you can make. Put 3 transistors together. Put your the smallest transistor together in that configuration. Put a largest diode which you can draw. I mean, so at least have to think how big your pixel has to be. Let's start with the number 10 micrometer. We can go with 1 micrometer as well, because we have 118 micrometer technology here, right?
Yes.
118 nanometer. So my transistors, the smallest which is available in this lab is 118 nanometer. So if I take 3 transistors, that's already 560 nanometers. 1 micron pixel will be difficult to make. Let's make it 10 micrometer pixel. So 3 micrometer by 3 micrometer pixel. So I already have the transistors, and I have got to fill the rest of the area with diode. And then I have to somehow connect these two. My pixel is done. And to be very frank, that is what we are going to do. But your challenge will be to draw these lines such that we're not going to do automatic layout here. Many of the digital people or analog people use automatic layout generation. We are one of the few people who still do hand layout. Because no AI tool, no automatic layout generation tool can give you the optimum. Our optimum is diode as big as possible and transistors coupled in such format and all those wiring done properly. Once we get 1 pixel, making arrays of it, you can done very easily. So we'll still do hand layout of each layer of the transistor. And we are done from pixel making. So today we finished at the active pixel sensor. This is called an APS, active pixel sensor. In more advanced technology, we'll have a 4 transistor active pixel sensor, and that is to remove noise. We have already seen our image is noisy. So we will not like to remove noise in software domain, because if it has gone all the way till there, we have already lost quite a lot of signal. So we like to remove the noise using a circuit approaches right at the pixel level. But for all practical purposes, the 3 transistor pixel will work. So whenever we start cadence, whenever I had a look at whatever technology is there, that's what we will decide. We will decide a 3 transistor and diode simulated to see it works. And then the main task will be layout. How do we lay it out such that, and we will run a design challenge between you guys. Whoever gets the most optimum layout, what's the prize we should offer? Okay, so whoever gets the most optimum layout will get a sponsorship for a DART fellowship to visit my lab in Germany. Whether you get it or not, that's open, but we'll certainly sponsor you for that. Maybe we can get a silver coin. That's good enough metric. For silver coin, I would have killed 5 people when I was in a very much less. So run a challenge on the smallest, most optimum pixel. But the pixel has to be DRC, LPA satisfied by the end of it, and it will be a layout challenge. Okay? Good. Any other questions? Any questions for the day before we end? It's already 5:30. The professor should always ask that question at the end of the day. By the time your brains are dead, what questions? Let me go home. What time should we start tomorrow? So we do 10 to 12 or 10 to 12:30. Okay? We break for an hour and a half. So that's 2.5 hours in the morning, and then we do 2 to 4:30 or 2 to 5. Happy? So unlike, you can suggest other timings. Okay? Well, my original plan is we do everything in the evening, 4 to 7. The professor said, well, Mudira said that's torture. And if he says that's torture, it has to be torture. Good. Thank Thank you very much. I'll see you all tomorrow, or some of you tomorrow.